welcome to the channel. Thank you very much for agreeing to come and talk to me and team. I really do appreciate it. That Anthony Riley's fucking stupid, eh?
Well, he won the award this year, didn't he? So,
Yeah, he was definitely done fuck of the year last year. He's trying again, even though he's so stupid he doesn't realise that he can't win it. You and Riley have had a bit of a falling out lately. It's been quite public. Do you want to say anything about why that's happened?
we just have a disagreement on this, this virus thing. So, he believes one thing, as do a lot of flat earthers, to be fair, and I just believe something different. It's simple. And unfortunately, Tony had this problem with the guest that I had on, the very first guest that I had on a couple of months ago, who basically laid out everything that essentially his plan has worked out just as as he said it was going to happen. And had a problem with that guest. He actually thought using a voice changer, and he very publicly called me out over it and said that I was dishonest, all the kind of horrible things. And I just thought, okay, well, I just released a very small clip of the video proving him completely wrong. There we go, and it all started basically. So we're at that point. Can I just say though, if my guests are watching and they're getting lag on the stream, just leave the stream and come over and watch it on Fight the Flat Earth, because I'm not sure what's going on, but for some reason, the last couple of times that I've done a stream, I've had this issue with bandwidth or something, so there's something going on.
Well, they are limiting bandwidth to people, I think, at the moment to cope with the extra people being home. So it could possibly be that, or it could be NASA trying to shut you down.
No, I put out last night when I did my gaming stream. They reduced the output on it, so it's site wide. It's nothing like directed at any one person. I think it's just site wide.
But I appreciate that anyway, Ranty. But anyway, why don't you just take a few minutes to introduce yourself to my audience, tell them what you do on your channel, why you're a flat earther, and then we can get into the discussion. So over to you.
Yeah, I'm sure he really knows me or has heard about me. So I do my own little thing on YouTube, essentially. Flat Earther for, what, 4 years now, maybe a little bit more. This is my second channel, was removed when I started talking about other things. Las Vegas, for one. But yeah, so I had to start off again, built my channel up again. I've got back over 5,000 subscribers, which is pretty cool. I do a round show table where I invite the Globers to come in and have a chat. There's no, there's no censorship from me over there, and a very laid back place for you to come if you want to express your views on, what you believe the shape of the Earth is. It's as simple as that. So I do my own observations. Have done, appeared on a lot of flat Earth streams, and thanks for the invite as well. You muted.
Yeah, sorry, I muted myself there. Thank you for agreeing to come and talk to me. I appreciate it.
At this.
It's good that you're coming to talk to me, because Riley refuses to talk to me now. I must have upset him or something. But anyway, so you're aware of the joke that we all have, that you're the best globe prover that we have. And the reason we say that is because the observations that you do, for us, it quite clearly shows something going over what appears to be a curve. So why do you think those observations aren't something going over a curve?
Because whoever does these videos, there has been quite a few, misrepresent what's being actually showed there. I go into great detail on not just my shows, but other people's shows to explain that. But the narrative gets lost. The actual evidence behind what's actually being showed there gets misrepresented in the worst ways possible, and the narrative sets, that it's the best globe proofs. Whereas in my opinion, and in Flat Earth's opinion, essentially a lot of my work has helped to progress the observational side of things. So I find it very frustrating when I get labelled that, when people just misrepresent the work rather than actually address it. We were talking in the pre-show about just being honest.
Yeah.
If you see something and you find that, that's a really good point, let's just move on from that, let's dig into that, I'll have a look, you have a look. But if you're just going to just lie about it all the time and misrepresent, you're never going to win with that sort of thing. And I know Conspiracy Cats likes to take the piss, it's his part of his channel, but essentially he's not really doing your movement any good by simply just mocking the work that I do, because essentially it's what a lot of flat earthers have come to actually rely upon and use it in their own observations, and has changed the mind of a lot of globe earthers too as to what actually is happening in these observations. So the work is very important. There's been a lot of work that I've done on this. It's been a lot of dedication gone into this. A lot of time has been put into this.
Yeah, I mean, like I was saying to you before we started, you've actually gone and done your own observations, which is something that I can respect. Majority of flat earthers that I talk to just tend to quote you, Sleeping Warrior, Nathan Oakley, and not do anything themselves. So the fact that you've gone and done the observations is something that I can respect. I think you're wrong about your conclusions on what you're seeing. Why do you think on the most famous one, which is the one that's on your channel, a boat did not go over a curve? Why do you think we're not seeing a boat going over a curve on that one?
A boat didn't go over the curve.
What was happening?
There was an inferior mirage in the boat. The boat disappeared beneath the inferior mirage. It's very visible throughout the whole. If you follow the boat from the start to the finish, you see the boat in its entirety. The further it goes away, you see an inferior mirage start off at the lower part of the boat. The further the boat goes away, it gets higher and higher and higher until half of the boat is inferior miraged underneath the rest of it. And I've been able to demonstrate on hundreds of different videos that the inferior mirage is not the Earth curve that you guys claim it is. It's not the edge of your sphere. It's an optical effect, probably caused by, I would say, evaporation more than likely, to creating this sort of like mirrored water layer or something like that. You guys would, well, including Rumpus, for instance, has claimed that now the inferior mirage that basically hides things. Most globers are on board with this now, that the inferior mirage will hide things. There's no actual edge of your sphere for that. But they will claim that it's due to refraction, that causes that.
Well,
and it's the, well,
the thing is,
all I was trying to say is that boat didn't go over the curve. The boat disappeared and it inverted itself all the way through it into an complete inferior mirage until it vanished into the inferior mirage. And I can demonstrate on hundreds of videos and hundreds of observations with plenty of documentation and proof that inferior mirage is not the Earth curve. It is just an optical effect. It's optical blockage.
Well, the thing is, one thing that I've been trying to kind of get across is that we don't see the physical Earth curve because there is refraction. We always see a distorted view of the horizon. And yes, there is optical effects, there is refraction, but the effects of refraction have been quantified. We know what the different temperature profiles and the delta of temperature over a certain height and the amount of change, we know what that can do to the direction that light is traveling. And when you say blockage by what? By just the light being refracted?
I wouldn't say that. I mean, there's no proof that it's the light that it's refraction that's causing that. There's no proof to demonstrate that. Bearing in mind, though, 2.5 years ago, it was the globe Earth's belief that inferior mirage, that clear line that goes through things that you see at the distance with an inferior mirage, that was the edge of your sphere. It was very clear. That was your argument 2.5 years ago.
I mean, I wasn't in the gig 2.5 years ago, and I've never held the view that what we see is the physical edge, because the mere fact that we have an atmosphere means that we're never going to see the physical anything. So we always see a distorted view of the horizon, and depending on the temperature profile and stuff, it can change what the effect is that we're seeing, whether you're getting an inferior mirage, whether you're getting some looming or towering or stretching. It just depends on the change in air temperature over a certain distance. That's what we call a lapse rate. And then when you know the lapse rate, you can calculate the coefficient of refraction, which can tell you exactly how the light is curving.
again, we're gonna disagree on that, because I see things as it would be like in a kaleidoscope. So everything that you can see, so you can see everything. It just gets jumbled up at times. Things will get jumbled up.
Yeah, but why does it get
I've never
jumbled
been
up?
able to. Well, there's a whole host of. If you look over a car when it's hot, you'll see that as you look over the hot surface, it
Yeah.
distorts the trees or the houses that you're looking through in the
Yeah.
distance. So
Or on a hot day,
there's
you can just see it coming off the road, right?
there's also,
Yeah.
you've got evaporation that happens over the ocean. I mean, that's
Yeah.
what forms the clouds. That's what gives us our
But
rain. You've
all
got a
those
whole. You've got
all those distortions that you see, they are all forms of refraction. Refraction is the consequence of light being distorted by the atmosphere in some way. And
well,
and
pollen in the air. Pollen in the air, for instance, particulates in the air. That wouldn't be forming refraction. That would just be blockage.
yeah, okay. So if you had particular bad air pollution, that would be blocked by like dust particulates and stuff. But say you're just looking out over the sea, you're not going to have much air pollution or pollen just at the sea as you look out. The main thing that's going to be changing what you are seeing is the temperature of the air above the water.
I don't know, actually. I'll be honest. I really don't think that's the case. If you look at how the motion of the ocean with all the waves, you get spray from the waves. You get
Yeah,
wind that goes across the waves that creates spray as well. You get evaporation. There's a lot of moisture that's happening in those lower 5 to 10 feet or so, just above the water. There's a lot of dynamic. There's a lot of things going on
right.
down there that can cause this kind of effect, especially at low down.
I mean, even light going through water molecules in moisture in the air, that's still refraction. Refraction is just a name for the distortion of light's path. Like my glasses, these are using refraction so that I can actually see. Your camera, when it's taking your photos, it's using refraction in the lens. The refraction is just a name for the distortion of light due to whatever's happening.
See, I'm not denying that light, what you look at in the distance, can be manipulated. It can be moved up, it can be moved down. You can see that with the Skunk Bay footage, for instance,
Yeah.
which is a very famous one. But one thing you won't see in there, you'll see all kinds of things in there. You'll see stooping, you'll see sinking, you'll see all the other effects of refraction. But one thing you won't see is looming. You never see looming in that particular, and that's my issue with this whole idea with refraction, is that I've never been able to see demonstrated to me, proved by anybody, Glober. I've asked for it for years. Proof of looming. Show me some proof of looming.
Well,
Um,
what do you define as looming? Because there is some kind of, I think, miscommunication between a lot of the groups, even between me and other Globers, as to the actual definition of what looming is. What do you define as looming?
Looming would be something that you shouldn't see behind an Earth curve being lifted up into your view so that you can see it above the horizon.
So it's just
So it
the
has to be behind something.
so it's just the act of something being lifted up.
Yeah, if I see, I've got plenty of videos where I've got down to just 1 inch, let's say, looking at 20 miles at some buildings across the ocean, right? And I've seen shore to shore. Right? Now, in that particular case, the Globers, including yourself, are going to turn around and say that that's been bent.
Right, just get the stream started. There we go, and I'll get Hangouts back up. I'll send you in new links for Hangouts.
Okay.
All right, guys, we should be back. I'm sorry about that. I had a brief power cut there. Okay, I'm just getting everything set back up so Ranty can share screens with me. Let me send that to you. I'll just quickly email you the link to that, Ranty.
Okay. Yeah.
I'm back.
Yeah, sorry about that. Dude had a power cut. Okay, right, there we go. All right, where did we get to?
I have no idea.
You were saying about looming, and you haven't ever seen any evidence of looming.
Yeah, I've tried to go out and I've tried to find looming. It's been. Oh, there we go. Finally got your link. Just 1 second. Let me join that. I'll leave this call. left that one.
Yeah, yeah. Sorry,
Yeah,
guys.
I've tried.
If you're just joining back again, I'm sorry. I had a brief power cut. We just get back on. We were just talking about looming. So sorry. On you go, Ranty.
Yeah, I've tried to find looming. Fortunately, I've got this place where I live. It's it's on the railings right next to the sea, so I can stand in the same position, put my camera on the railings in the same place, and I can see a post that's 4 miles away that's in the ocean. It's got a little star on it. It's like a little star marker, and behind that, some 18 miles away, is the buildings of Barrow. So you've got Devonstock Hall, etc., that are over there. And every single time I've filmed from that spot, I've never seen any change, whether in their relative positions between each other. They've always been in an identical line. It doesn't matter what you know. There's no change ever in any of it. It's always in the same position. So you've got a marker that's in the same position. You've got the buildings that are in the same position. I'm filming from the exact same spot. I'm going at the same sort of times with the same sort of tide heights, same sort of weather conditions. It doesn't really matter anytime. It doesn't really matter. Whenever I go, I never see any difference. Those posts, the post and the building are always in the same spot.
Right. Oh, so are you denying that looming exists at all as a form of refraction?
I'm yet to see evidence of things being loomed up. I've been able to see things being pulled down and stretched and compressed. I've seen evidence of that, but I've never seen evidence of anything being loomed up.
Like, what about the famous footage of the shoreline where you can literally see it rising up and down? Isn't that you seeing it looming and then going back down? I mean,
well, no, it never starts off looming. It starts off in its natural position. It starts. You're talking about Skunk Bay here, so
yeah, that's the
it
one.
starts.
Yeah.
Yeah, it starts off in its normal position, and you see movement down and then back up, and then down and back up, and then down and then down, 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 and then back up again. You see a lot of that, but you never see it the other way. You know, I mean, I actually have a video of that where I've got the tree lines all lined up with the lines going across, and you can see that the trees are going down and then they're never going back up past the relative position.
So there's a form of refraction that pushes things down but doesn't bring it up.
Well, of course it resets it, so you could always say, I suppose you could say that it's going back up again, but there's no demonstrated proof of something being loomed up from beyond an Earth curve. Right, that's the main thing. I've never been looking at a hill or expecting other people to look at a hill and expect to see something from the other side of the hill suddenly pop up. You could film it for the next 20 years and you would never see a house. If there was a house on the other side of that hill, you would never see it ever. You could film it for 100 years. I don't care how long you film it for. It's never going to pop itself up and be seen. And this is what I'm asking for. I'm asking for proof that there's some kind of curve there. Doesn't matter how you can create some kind of watery curve. Show me something being loomed up from behind it.
Okay. I'm actually working on something.
And bearing in mind,
that, but my question
bearing
is,
in mind, it has to be loomed up in proportion too. And not just in proportion, but it has to look like there's something. So whenever you see these buildings, I've gone down, I've seen these buildings 18, 20 miles away. I've filmed them as far as 24.5 miles away from 2 feet. Now, if you can show me something that's been able to loom up that in its relative position, with all the windows and the buildings and the chimney stacks and everything just loomed up in proportion, without any, this is what I'm asking for, not some smudge, something that you can discern as a building. When you're looking at Red Pill Philosophies videos, some of my images, plenty of other people that have gone out and filmed these distant land masses and buildings, when you see them in proportion and there's no distortion between them, that everything's in the relative position, show me that being able to be happening, and I will jump. I'll be a Glover, but I'm telling you now, you'll not be able to do it.
Right. Okay. So obviously I can't show you that right now myself. I am working on doing something which could show that. I
Don't
don't
worry.
go out. I don't go out and
I've
do
been
the
asking for it for
observations.
3 years, so it's
But
fine.
I don't go out and do the observations, so I don't have something that I can just refer to and do that. I mean, I've been looking into the nature of how refraction works. But now, your claim is that it always pushes, it would push things down rather than bring it up. What is the cause of things being pushed down?
Well, again, I'm not of the belief that light is a ray. I don't believe that light is a ray. I
Right.
believe we see things more of as like a projection, in the distance. I mean, if you look at somebody else looking at something, you don't see light rays going from the object they're looking at to their eyeball. You don't see light rays go into them. So the idea that there's light rays, I mean, you think of it this way, right? If the light rays always hitting your eyes and you just stare it front ways, right? And you're not focusing on the outside of your eyeball, you're focusing dead ahead. You've got all these light rays coming towards you. The idea is that all these light rays, only one light ray that always just hits your eyeball, so you would have a full mapped image of everything. You wouldn't have to focus because you'd be getting all these light rays at the same time. We don't see that. You have to focus on things to see things. And we never see a ray. And you can see man-made rays, lasers.
I mean,
Lasers, and you can manipulate them.
Light isn't a ray. Light is a wave. It's a potential. Team, do you want to explain what light is? Because you're far more versed than me.
Well, let me just say that there is a massive argument going on whether it's a ray or a wave, or whether it's something different. So, I mean, this isn't going to be just sorted out here and now, because even in the scientific community per se, there is still a massive argument going on between scientists about this particular argument. So, we can both agree to have our own opinions on this, but there's no clear winner in this argument.
Team? Is you there?
Well, I mean, light's just it's just a potential in the electromagnetic field. It's been experimentally proven to be so. I guess I would need to know more what you mean by light as a ray. I mean, just could you elaborate a little bit more on that, Ranty? Like, tell me in layman's term what you mean when you say that light is a ray.
Somebody has a laser beam, and they shine it 10 miles across a lake. You can follow that trajectory of that light because you can see it. You can see that light beam the whole way. That's what I would class as a light ray. Same as if you manipulate it in a water tank, so you're able to.
Yeah, okay, so let's say we have a laser inside of a vacuum where there's no particulates in the air. Do you think you would still see the laser light?
I have no idea. Show me that experiment.
So like, well, let's say you're at home and you turn on a laser and there's like nothing in the air to reflect the beam of light from the source to the wall, let's say. Are you under the impression that you would see the laser beam even if there's nothing for the light of the laser beam to reflect off of?
I don't know. I mean, again, it's something that I've never tried, so I don't know.
Well, okay,
perhaps you've got a video that can show me that.
Yeah, basically, it's as simple as just saying, like, if I was to take a pin laser and shine it on the wall, you wouldn't see, there would need to be something in the air for you to see the light coming from the laser pin to the wall. Otherwise, you'll just see the light on the wall. When they turn the laser on, you just see where the laser's pointing. You don't always see it unless there's something in the air to reflect the light back.
So you mean that what you're trying to say is that the laser itself, the reason you're seeing the rays through the laser is because they're coming off little dust particles or something that are in the air, yeah?
Yes, that's what I'm saying.
Okay, so
that's why,
have you been able to?
If you watch like movies, and you'll see like, and I'm not saying this is the way they are, but to give you an idea, when somebody's trying to sneak into a building and they've got the laser security system and they pull up powder and they blow the powder on the laser and it lights up where the laser actually is so they don't cross that path. That's similar to what I'm saying. It's like, for you to be able to see those lights, you actually have to have particulates for the light ray, now I'm using light rays, for the beam to bounce off of. They're individual photons in a laser.
Okay.
It's not, it's not like it's a, let's say a string, for instance, like we pulled out a string and attached a string from the laser source to the point that it's on the wall. It's not similar to that. It's actually photon packets that are being emitted.
Okay, so you agree that there's photons, yeah?
Yes.
Okay, so when would you say there's particulates in the atmosphere on a sunny day looking across to a distant building across some water?
Yeah, there's always going to be particulates in the air.
Okay,
Always.
so why
Now,
don't we
depending
see?
upon the particulate. Well, okay. So,
So,
for instance,
so if I'm
we
looking
can
at
both
something
agree.
else,
Can we both?
Sorry.
Well, we can both agree that atmosphere is filled with different atoms, right? Like we have oxygen, nitrogen, argon, and a few other, trace elements. But it's all a bunch of different elements that are in the air. Those are particulates. Whether we don't, see them as particulates or not. We're talking when we say particulates, we're talking about solid objects that are floating around in the air. But really, even molecules are in the air. The light just passes through some things. It's not affected. The light, let's say the oxygen in the air is not affected by the light that comes in. Like it's not heated up, it just passes right through it. It might get refracted, the light might get refracted, but it's not reflecting the light. You know what I'm saying? It's just passing through the oxygen molecule. Whereas some things don't have the ability for light to pass through them, they just reflect off of them or absorb them. Like water, for instance, does have the ability for light to pass through it. It doesn't pass through it the same way it passes through air, but the light does pass through it. So you could say that water is a particulate that it's not in the air, but it's a particle that allows, when it is in the air, light can still pass through it. So, but it's still a particulate in the air, but it's just different than, let's say, like dust in the air, where dust would actually reflect the light instead of have the light pass through it.
okay, but going back to what you said about the laser and sort of like ambient light, I'm going to call it ambient light now. So you're looking at a building in the distance that has ambient light. What gives us that? What gives us the means to see that ambient light in the distance?
Do you have a picture that I can see? Or,
Anything. There's a picture
I'm sorry.
behind me.
I'm sorry. I thought you had. Yeah. I thought. Okay.
Yeah,
So the picture behind you. What are
yeah.
you
There's an
looking?
ambient
What's the
light.
ambient
Any
light? Let me
pick a
full screen
building.
it.
Pick a building. Pick a building. It doesn't really matter. Just pick any building that's on that screen behind me. That's ambient light.
Okay.
If you're looking at that, if you're on a hill and you just see some houses down below, what is the means of
Are you talking
transporting
about at
that
night?
light?
At night or during the daytime? At nighttime, you're talking about?
Daytime.
Daytime. Okay. Well, so we're not really looking at. Okay. So in this particular picture, it appears as if the sun is overhead. Correct? I mean, I'm not. I don't want to make any assumptions because I don't see the sun in this picture, and it looks like it's
I'm not
daytime. So
seeing.
I would assume the sun is
I don't,
overhead.
I don't know what I'm not. I have no idea what you're looking at.
I'm looking at fight. Am I looking at something I'm not supposed to be looking at? I'm looking at Ranty's screen
You're just
right now.
looking at the picture on on Ranty's screen, but I think he's just talking about any building in general, right? So, how do we see the light from that building? Is that what you mean?
Yes.
Well, yeah, the light hits the building and reflects off of it, and then you see it. You see the reflection of the light.
But you would say that would be the same process as a laser, though.
Well, okay, a laser's a little bit different. There's different processes they use to make the laser appear as a beam and travel as a beam. It's still individual photons that are in the laser. So what we're looking at is a light source, which we can treat as a point light source, which is the sun, shining down in all directions. So that when the sun hits the top of the roof, let's say, and the light bounces off, it bounces off in all directions as well. This is how any observer that can actually see that point can see the point because it's being lit up by the sun.
Okay,
And
so
that's how you see it.
there's two trains of thought here. Obviously, I'm saying that things that we see in the distance are more of a projection, and you're saying the photons that are coming towards you, which will give you this wave function that will allow for refraction. Yeah.
Yes.
Okay, fine, fair enough. Okay, so how would you think things would work on a flat plane? With your particular idea about how photons work through the gradients.
Well, if you could set up an experiment that was well controlled and, to where you could, let's say, define over a large area controlled gradient, okay? Well, if the reason why we have refraction in all directions, number one, is because we have a curved Earth. So any tangent to the line, let's say tangent to the surface of a curved circle or of a circle, is going, if you build a gradient from the surface of that circle out, and let's say we say every 1 centimeter we use a different color marker. Let's say we go from the circle being black to a red circle, to a yellow circle, to a green circle, to a blue circle. If you draw a tangent to the circle, then that tangent, as it leaves the surface of the circle, it will, as it travels straight, it will pass through different gradients. So any straight line on a circle, on the surface of a circle, is naturally going to pass through different gradients. On a flat Earth, you could set up a controlled experiment to where a straight line should travel through non-gradient atmosphere. There would still be a slight gradient because we can't absolutely control everything and make it a perfect mixture. But at the same time, if it was a flat plane or a flat surface, then we should be able to see different effects due to refraction because you're not actually going in a straight line. And here, let me pull it up on Paint because I don't. That's a good concept. I want to show it real quick, but without confusing what I'm saying. Give me 1 second. It'll just take us.
What if somebody like Mick West or the Rumpus had already performed this sort of task inside the fish tank and was able to gradiate the tank and show that a laser beam being manipulated through it, arcing, curving?
Yeah. Give me 1 second. I'm getting that picture ready for you, Ranty.
Yeah.
I just want to kind of show what I'm saying.
I've been emailing back and forth with a guy called Dr. Andrew Young, and he's created a simulator of refraction, and he's actually got an entire page about if the Earth was flat and what we would expect to see. I'm just trying to find that so I can put it up for you. Because like Team was saying, if the Earth is flat, then the gradient of air pressure is going to be flat as well. So that there's going to be no curve to the gradient. So you're gonna, when you're looking, you would be looking through one layer of air continuously, and it wouldn't be a change in temperature. I mean, there would be variations the closer to water you got, because the temperature above water can change quite rapidly, and that is what gives us different refractive effects. But if you moved away from the higher lapse rate of being near water, then you would basically be looking through the one density and temperature of air as you looked out, instead of the natural curve you would have if we are on a globe.
I'm almost ready, Fight. Give me 1 second. I'm going to share my screen for you in a second to get so I can visualize what I'm saying right here. Let me just add this input. Again, I have to redo everything from the start because I reinstalled vMix and rebooted my computer and formatted and shit. So I have none. Bro, I'm realizing how much shit I'm missing right now.
You're going to have to set everything back up from scratch. But sorry, Ranty, you were going to say something there?
From scratch.
Yeah, you see, I've already been through this with McToon, with Rumpus, with Stingray, who have modelled it and done experiments on this and have proved and stated categorically that on a flat plane, you would get these gradients, the light would be bending down under certain conditions. It would be disappearing from the bottom up. What have you got to say about that?
Right, can you show my screen?
It depends on the conditions. So, like the closer you are to the water, the more refractive conditions you're going to get, because the more rapid changes in temperature you're going to have. So you would still see some refractive effects, but you definitely wouldn't see as many as we do.
Okay.
How would you
Ranty,
be able
are you showing my screen? Fight?
Yeah, showing your screen.
I'm sorry, go ahead. No, go ahead, Ranty. I'll
Yeah,
wait till Ranty's done with that.
It's just that you made a claim there that that it wouldn't be you wouldn't have as much as on a globe. Can you prove that?
Based on our knowledge of refraction, the model says we wouldn't have as much. because the way that we say
Yeah,
refraction works.
I can explain it.
Yeah, right, Team, go ahead.
Go ahead. I can explain it. Yes, the reason why we say that you wouldn't have, let's say all things are the same, okay? Whether we're looking at a globe or whether we're looking at a flat Earth, we're just going to say, let's say the atmosphere is modeled the same way in both. Okay, on a flat Earth, you're still going to get generally, if you take a straight line, right, on a flat Earth, and you take it in any direction and you keep it at eye level, let's say, and you make it for sure level with the surface all the way, okay? Well, that line is going to be straight, and it should remain in the same atmospheric, conditions all the way across. Like, it shouldn't, you're not going to get a difference in elevation where on a globe you would, where the straight line would actually take you into higher elevations as you continue straight. So then those elevations at a future point in the line, the pressure will be different, the temperature will be different than what it was at the starting point. Whereas on a flat Earth, if you take a straight line at 6 feet off the ground, let's say, that straight line all the way straight will always be in the same amount of atmosphere, roughly. Like I said, if we say all things considered, if we're dealing with an ideal situation here, then it will never go into a different gradient of atmosphere. Therefore, the refractive index, which is N, would always be the same.
That's ridiculous. That's ridiculous.
No,
I mean, you've got one line in. You've got one line in there. Yeah. Okay, so you see the blue line at the top that you have. How does that photon get to your eye?
Okay, are you? Yeah.
How does the
Are you
photon
looking
get
at my?
So in order,
Okay.
So in order for that photon,
are you looking at my picture?
Yeah,
I am, yes.
he is, yeah.
In order for that,
let me explain it first, and then.
Let me just ask you.
The blue represents a layer of atmosphere. Okay, so the blue represents just a layer of atmosphere. Let me explain what I'm looking at here, and this is the only reason I was saying. In fact, you know what? I'm going to give you a second one too. That's just going to go like this. Let me change that. Hold on. Okay. Well, first I will get to the second one in a second. Let me show you what I'm talking about here because I just changed that color of that line. Okay. So now I tried to move it. Okay, you saw it was blue. The outside circle was blue, right? So the black line going across the top of the inner black circle, which is hard to see, it has a red circle outside of it, a yellow circle outside of it, a green circle outside of it, and then there was a blue circle, which is now black. Now that line, each one of those circles represents basically a different elevation, different pressure, okay, different atmospheric pressure, different temperatures. But that line, you see how the line, as it goes on its tangent to the inner circle, it passes through the red, then through the yellow, then through the green, and then it's a black circle now, but it was blue, and then through the blue circle, okay? So it goes through different gradients of air pressure. On a flat Earth, let's say, let me give you a flat Earth right here and explain. Here's the ground, we'll say, okay?
Oh, I need to zoom back.
Here's the ground. Okay, we'll go right there with the ground. We'll say black is the light. Oh, let me make that green real quick. Then we'll say black is the light. And I'll make it black in 1 second. Black is the light, and then we have red, yellow, green, blue. We'll just go red, yellow, blue. Okay. What about green? I said, just go there. Okay. Light's yellow. I'm sorry, I don't work with paint very often. But let's say here's the next different gradient of atmosphere, which would be red. And then we'll just go green after that, or whatever. I suck. So ignore my shitty artistic skills here. All right, and we'll just say blue since we don't have that color. Okay, so the yellow light, if you'll see, if the yellow light stays equidistant to the green line, which is the ground on a flat Earth, we'll say, it never goes into the other layers of atmosphere. So therefore, it's not going to have a lot of the refractive indexes between the two sides of the Snell's law, okay, the N on both sides is going to be equal to each other.
I'm sorry,
and that's going to change the ultimate refraction, the amount of refraction. Okay. What's rubbish about it?
Okay. So you see the yellow line that you have?
Yeah.
See the yellow line? Okay, so can you put somebody's head on that yellow line on the left-hand side and pretend that that's where they're taking the observation from? Okay.
There you go.
So now we've got on the right-hand side the top blue, the top blue line. So that's say the top of the tower, right? So that's the light ray coming from the top of the tower. But it's not just one light ray. You have millions of light rays, millions of these photons going in all different directions. Only one of them will reach your eyeball to give you the actual image that you're trying to look at. Now I want you to show me that light ray, where you've got your cursor, traveling to that person's eyeball on the yellow line. Show me that. Draw a line in a line from where you are now, from where it sets off.
Okay.
Yeah. Now
So
now put a line.
I'm gonna change the color. Yeah, I'm gonna change the color real quick, and I'm gonna make the assumption that this is your point light source, right? That's what you're basically like. It's a tower. Let's say a lighthouse at some distance. This is the top of the lighthouse. Are you okay with that analogy? Yeah, I'll assume you are. Okay, so light from this point source will. Okay.
Randy's disconnected.
Let me know
a
when
sec.
it comes in. Okay. So.
He'll come back in a sec.
Yeah, I'll get finished drawing my.
I think the point he's making here is that there's still it's still going to be going through a gradient, depending on how high it is.
Yeah, I think he's saying that this line right here is going to pass through different gradients.
Yeah, right. Sorry, Ranty. Welcome back.
Okay. So my point is very simple. You've got all those light rays going from different. There's only one light ray that's going to actually get to your eyeball on the yellow line, and that one will have to have changed from the blue through the red gradient down to the yellow gradient. So it is going through the gradient.
Yeah. No, understood. But that's why you do things. Why you don't look at two things that are at different heights. It's why you go up to like the Miles Davis observation is done, where the camera height is at the same height as the top of the was it the bridge or is it
the tower of the bridge or Hopeton Monument. But you are right, Ranty, that there will be a slight gradient there. But now imagine those gradients curving, and it's going to be even more, isn't it?
There will be a gradient through all of the layers apart from anything that's exactly parallel to your eyeball. Anything that is if you're 6 foot, if your eyeball is at 6 foot above the water, you will only see the only thing that won't change or have a deviance is the one light ray that reaches you, that one photon from the same height that of something that you're looking at in the distance. Every other ray will have to be going through a different gradient.
Yeah, agreed. But my point is
but I just want to confirm, because Team Skeptic said that all the light rays are just going to go parallel, but never going to change.
No. I was talking about. Hold on. Let me answer that fight. I was talking about two observers at the same height, Ranty. I was talking about. Let's say you had an observer right here. I'm in the line. Let me draw a circle. I was simply making this statement. That you take two observers that are at the same height, then that line should stay. Then a direct line between the two should remain in the same general atmospheric conditions. Therefore, the refraction would be minimal, if not none. In an ideal situation, it would be none. But since we're not dealing with an ideal situation, on a flat Earth, it would be more minimal than it would be on a globe Earth. Because the globe Earth is rounded. The tangent to the line, no matter where you draw this line, like we could draw this line even higher in elevation, and it would still pass through multiple layers, even though it didn't touch. It didn't touch
as many.
It would still pass through multiple layers.
Yeah, but I just want to confirm too that the process would still be the same when you're looking at distant buildings or something. If you're looking at the chimney of something that's 2 miles away, that chimney that's 34 or 40 foot high is going to that light ray that's coming to your eyeball. You as a 6 foot human, it's going to be changing. It's going to be going through the denser gradients.
Yeah,
it has to.
Okay, so let me ask you. I think I'm finally getting it, Ranty. Hold on. Let me see if I can confirm what you're saying. Well, I want to ask you because but Ranty, here's what I'm going to bring to your attention here, okay? Because in the Miles Davis observations, there's still no explanation for what you're saying. Because I do understand what you're coming. Let me draw this out just real quick, okay? Because I think it won't take but a second to do this one. Yeah. Okay, so we have the mountain right here, right? We have a mountain right here that's taller than the observation, right?
I've actually got that.
And then we have an observer here. Well, let me grab this circle. We have an observer here. And we have power lines that run up to about right here. We'll just call this that the center of the circle and the top of those power lines are the same. Okay? So, now let me draw another line, let's say that just goes through here. Okay, now we're going to make the assumption that the top of that line ends at the top of that because I'm not a perfect artist. But, okay. So that we're going to say that's where the camera's at. That's the top of the poles. That's the mountain in the distance. The physical mountain appears to be lower, okay? The top of the mountain appears to be underneath where that yellow line goes through. Now, if what you were saying was correct, if it was flat and it was simply, and we were at the middle of the mountain where the line of sight intersects the mountain, that should still be at eye level. Because that's going to be going straight. That's not going to be coming through different layers of atmosphere to get to you. That's traveling straight.
Well, are you denying sinking?
What do you mean by sinking?
I think he means refraction making things drop down.
Oh, no. Refraction can make things drop down, sure.
Okay, so yeah, I'm just going to say
because
up.
It's not a single.
Yeah, but can it make things rise up? Can it make things rise up from beyond the Earth curve? That's the thing. And I've got an image to show. I've got an image to show you.
Yeah. Okay. I'll go over to
Have you not seen boats floating in air? Like they get risen up quite high in elevation to the observer, relative to the observer. I mean, it's an optical illusion, but yes, I mean, absolutely. I've seen many pictures and videos of boats that look like they're floating in the air, and we both know that the boats are not floating in the air.
Can you see my screen?
Yes, we're showing your screen now.
Oh, let me get to it. Let me get to it so I can see it.
But can I just say that you are right that if you look at something that's a different height from you, then there is going to be a slight lapse rate. But now imagine that the globe, that your sight is curved, then it's going to make the amount of layers it goes through even more, which is why I said on a curved Earth you would get more refractive effects than on a flat Earth. Because you would go through more of a gradient than on a flat Earth.
But all I'm saying is that it can be equally scaled on both. Whether or not one's has a greater scale as opposed to the other, to simply just say that you can't have these refractive effects, this sinking effect on a flat plane is incorrect.
All right. So...
Yeah, no, I do think you should. I do think you can. I do think you can. But why are we not seeing the sinking effect also on... But Ranty, what I'm saying is why are we not seeing the sinking effect also on the power lines in front of it or the towers that are in front of the camera? Why are we only seeing the sinking effect on the mountain itself?
Are we talking about Miles Davis here?
Yeah,
I'm talking about Miles Davis. I was assuming that you were talking about the sinking being the mountain in the back sinking below the line.
So like on this one where the camera height is 210 meters, and you've got Hopeton Monument there, which is 210 meters. Yeah, you've got the mountains in the distance that are more than 1,000 meters above sea level, falling below that tangent of 210 meters. Mm-hmm. So is it your contention that it is a form of refraction that is doing that?
It's possible. Who's to say it? I mean, first and foremost, you've got to demonstrate that Miles is exact. I know it's measured and it says that that hill is 210 meters high, but let's suppose if that survey was done 25 years ago, let's suppose that it's not 210. It could be 205. It could be 215. Who knows? I mean, there's a whole lot of variables going on there, you know.
Well, Randy, as a person who does a lot of experiments...
Yeah, but we'll go with it and say, okay,
as a person...
210.
Sorry, go on, Ranty.
And, you know...
Yeah, go ahead, Ranty. I'll wait for you to get done.
Okay. So we'll go with it, and we'll say that, okay, let's say that he is at 210, 210. You know, I mean, we'll take his word for that. All I'm going to say is ultimately it's such a high elevation. It's such a high elevation, and it's really tricky to get that kind of data. What I can show you here is different. I can show you something very, very easy. The camera height was, well, to the center of the lens was just 2 inches off the ground at 100 meters exactly. And you can notice that, I mean, that 2 inches is just at the bottom of where this smile is on the conspiracy cat's egg on the right hand side. And what you'll see is that outside of or below, anything below that 2 inch is stretched downwards. You can see that this is being pulled down, the image is being pulled down, but anything above the center of the lens, above the mouth, it is kept relatively in proportion. Nothing really changes too much on that. There's no stretching upwards or anything, but there's clearly downward. There's a downward stretching going on this image. It's very evident.
I don't think anyone would deny that you are seeing a downward stretching in that image, but my question here is, well, more of a statement, that you're going to get very different effects above a racetrack like that than you do above water. You're going to get, you're more likely to get temperature inversions on something like this when the ground heats up a lot more. Whereas above water, you're going to get, quite normal to have a colder, denser layer of air just above the water that then changes temperature quite rapidly the further you go up. So I don't think anyone would deny that you can get these as the effects of refraction. But if you can stretch things down, then why can't you stretch things up as well, or loom them?
Well, here's another image. One of your guys as well. Al K, I believe it is. Or no, it might have been Miles. No, actually, I think this was Miles Davis as well. This was Miles Davis's. It's very clear here. You can see the stretching again over water. You know, it's very evident in the comparisons down here. Let me see if I can scroll in to show you. You can see that this ledge. See this ledge on the right hand side. The lower down you go, it's scaled to width, so everything's in proportion. The height's the same at the top. And then this ledge on the right hand side gets severely stretched. You can see where it gets completely stretched down here, and that red line should be from the higher elevation. This was a higher elevation on the left, this was a low observation on the right, and you can see the lower down you go as this stretching appears. You can see that the image has definitely been stretched, and on the left hand side too. So it's very evident in Miles's own footage. This is over water too.
Again, like I said, no one's denying that you can get those effects of refraction. But if we knew the temperature of the air at those points, then we could accurately model it out and show you what we're supposed to see. But you're saying that they're stretching down, and yes, I agree in that what you're showing there appears to be stretching down, and on the eggs there is stretching down. So if you can have stretching down, why can't you have looming? Why doesn't that work the other way as well?
Well, I'm not saying that you can't have an image, anything that you can see, right? So I can see this rock. I can see it. There's no denying that rock is there. I can definitely see it, right? Yeah. We know that as you look through atmosphere, weird things happen. Your Skunk Bay is a perfect example of that. The moving up and down of the rock or the tree in the distance. You can definitely see that. But it's my contention that something that you never see, you can never bring something up from behind something else. It can never be demonstrated. I've never, like for instance, if you were down here with this rock in the foreground, so this is another island on the right, in his line of sight, right? I imagine if Miles Davis sat here forever, he would never see something beyond that loomed up. Doesn't matter how long he sits there, he would never see something loomed up in front of that.
So you're saying it's impossible. It's impossible to loom something up from behind something with using refraction.
Yeah, I mean there is a butane experiment that is so screwed up in many different ways.
I mean, it is refraction, though. It is showing that refraction can
well,
loom
not
something up.
really. Hang on, I might have an image of that. Hang on, let me just see if I can find that. Just 1 second, because I'm sure I've got that
I might even
somewhere.
have it here. Let me see.
Here we go. So let me open this. So this is the butane. This is the butane footage. So
yeah,
here we go. So we've got on the left-hand side, we've got the with no butane put on it, and then we have butane put it on the right-hand side. Now the camera never changed position, and you know, I took screenshots of each in their individual positions. You know, so nothing was changed. There's no scaling difference. Let's go to the next image. What's very clear in this is that the only thing that's changed is this red thing, this red part of this plasticine has moved up. But look at the green. That didn't loom up. That didn't move in proportion. Now, if it was genuine looming,
it wouldn't move in proportion because you would be looking through the gradient of what was created. Now, what happened when the butane was put on there was it chilled the air to about 0 degrees centigrade. That's the temperature of liquid butane, right? So that means that as that liquid butane pours around that pipe, it's going to create a gradient of temperature, which you're going to see through, which means that the closer to the pipe you are, the more refractive effects you're going to see. So you wouldn't expect the green, which is further away from the pipe, to move in proportion because it's going to be further up in the lapse rate.
Yeah, I understand that. But this is my final point, which is what I'd said to you before. I want things to be loomed up in proportion. I want things to be as you see them. Like, you look at a building in the distance, you know you're looking at a building. I look at this here and I see a shine on this. I don't see in the right-hand part, this is the control image. This is the image that he takes, and this is the side that you're filming. You see all these different indentations on the actual plasticine and stuff.
Yeah.
You don't see that here. It's smudge. You know, this is something that can happen. You can make this plasticine appear in the image. You can't make it appear in the image in its entirety, exactly how you would look at it. So if this was a building that I was trying to see that was being loomed up beyond the earth curve, I would just see a smudge. I wouldn't see windows, I wouldn't see doors, I wouldn't see a chimney, I wouldn't see people walking on the sidewalk.
Isn't that more to do with really bad quality of the image there? I mean, you definitely are seeing looming. You are seeing the red being brought up above the horizon of that pipe. You're definitely seeing that, right?
Yeah, you're seeing a smudge of something lifted up. That's not a demonstration of looming. You know.
Well, looming doesn't have to be a perfect replication.
Yeah, it kind of does, because if you look at the imagery that we put out, us flat earthers put out, when we see shore to shore over 20, 25 miles, and we see shore to shore, we see objects, buildings, windows, you name it, everything. You get street lamps. You know, you see these things in proportion, and not just in proportion, but in proportion the whole length of the image that you're actually filming from. Red Pill Philosophy has a really good video out where he films from, I think it was 6 foot observation height, and he can see cars some 18 miles away, just 6 foot above the water, and the headlights and everything. I mean, there should be like 100.
I'm not denying that those observations exist. They definitely do. If they came with accompanying data, like, you know, the air temperature at certain levels, then we could mathematically model it out, because the effects of refraction have been quantified. It was done by Gauss using theodolites and kind of pointing them up at certain angles to figure out where the light was meeting each other. You know, and it's been experimentally done throughout the years, so that we know how refraction on our globe, you know, in the air works, because it has been quantified.
Okay, well, if it can be experimentally proven, why is this the only proof of what I'm asking for? This butane experiment where we've got this smudge.
You've seen Mr. Sensible's thing, right?
No.
Right, well, let me show you that. You understand the magnifying glass uses refraction, right?
Let's have a look at what you've got to present.
Right, okay, so Mr. Sensible did this, and what he's got, he's got the side so you can see, and just beyond the horizon of this ball is the blue, which you can see if you look at the top right. And on the windowsill in the distance, there's a little tack with a bit of white paper on, okay? Now, what he does is he puts a magnifying glass in front of the camera. Come on, get to where you do it. Right, here you go. So he puts a magnifying glass in front of the camera, and it literally looms the horizon of that ball up. So you can see some of the blue of it, and then you can see the white of the paper in the distance behind. The further you are away, the less that you can see it, but you can quite clearly see in proportion the horizon of that ball being lifted up, the blue of that ball, which isn't visible at this point, but then is when he puts the magnifying glass there.
Yeah, I'm not too sure what I'm supposed to... I'll be honest, I'm not too sure what I'm looking at here, but it looks to me anyway like his magnifying glass isn't straight. And with the fact that it's actually just angled ever so slightly,
I think you can see on the picture in the top right, he's got it pretty straight.
Let me just
play you.
You will see that it's tilted.
Let me just play you the entire video because he kind of explains what he's doing.
Okay, Black Swan Killer. Over here.
I can't hear it.
Oh, you can't hear it.
We have a little tack.
One sec. Which one was that? Bear with me.
Paper on a little flag.
Oh, I know why I haven't put it through the audio bus. Here we go. You should be able to hear it now.
Over here, we have a little tack with a white paper on a little flag. Here we've got our sphere with our platform on, and we've got this blue area which is beyond the horizon. It can't be seen on the close-up footage. So what we'll do is we'll introduce some refraction. I'll keep the camera running in the corner so you can see the whole thing. So we've got our view of the platform just in front of the horizon, the physical geometric horizon, and you can't see the blue which is beyond the geometric horizon, and you can't see the white flag either. Here comes our refraction, distortion. There's the platform, and as we change it, you can just see the blue that's beyond the geometric horizon and the white flag behind it. There it goes. Here it is. Refraction will bring things beyond the geometric horizon. Black Swan busted.
No. He's moved the position. Right, that his what's it called? Magnifying glass. His magnifying glass has a direct line of sight to the damn tack, and all you're doing is looking at the magnifying glass. That's ridiculous. That's the worst thing I've had. Honestly, I'm sorry, guys.
That's exactly
really
Ranty, but that's exactly what we're saying happens in the atmosphere. The atmosphere has a direct line of sight to. Hold on. The atmosphere has a direct line of sight to the object, right? That's beyond the physical horizon. So the light coming from that object goes to the atmosphere, and in this experiment, that would be the magnifying glass. And the person, the observer, that can't normally see beyond the geometric horizon can now see through it, can now see beyond that because he's looking through the atmosphere. That's exactly what we're talking about.
So all I'm saying here is that you've presupposed a ball, firstly, and presupposed that this is acting like the atmosphere.
Well,
right?
No, I mean, in this experiment, they haven't presupposed the ball. They've literally got a ball, and they're showing you that you can see on a ball that the physical, what is beyond the physical horizon, can be brought up using refraction. And you're right that the magnifying glass does have a line of sight, but then it's using the refraction to meet that with your line of sight.
Yeah, but the same thing could be shown when you stick a ruler in a puddle or a glass of water. You'll see that it changes its direction too. You know, I mean, this proves, to be honest, this proves nothing. But what I would say is that if you remove that
proves that
ball,
it's possible. It proves that it's possible.
Just one thing. Yeah, listen, I'm not saying that it isn't possible. I want to see a demonstration of this in reality. This is a test. This is a
Look at all your
ball in the way of
videos.
something.
Look at your
No,
videos.
hang on,
You
there's
do,
no
hey,
need to.
Ranty, you do an amazing
You're
job.
doing well
Hold
up
on.
to now.
I'm not trying to
Now,
insult with you. I'm not trying to insult
okay.
you. I'm just trying to say, like, you do a very good job of demonstrating what you're asking to be demonstrated.
So if you remove that ball from the image and you just have a clear line of sight at it, we don't need any refraction for that
No.
in this image.
But that's
Yeah, we
that's
just
the
see
point
it.
of putting the ball there, so that there's a physical obstruction, and it shows you that you can bring something above a physical obstruction, which is equivalent to us saying that something that should be hidden behind the curve can be visible because of refraction.
So now show me that in reality.
Well, that is reality there.
Over, over water, you show me that same thing happening beyond Earth curve.
Well, the Chicago skyline being seen is a great demonstration of that. Because you shouldn't be able to see
Really?
that if the Earth is a globe, right? If the Earth is a globe with the
Exactly.
circumference that we see, yeah. But then on certain occasions
Then
you
that's all
can
need.
see it.
That's all you need. That's all you need.
But then on certain
But isn't it
occasions
just-
you can see the Chicago skyline, which is a
But on other
demonstration
occasions-
of it being
What?
brought up. On other occasions you can, absolutely.
Why is it being brought up? Why is it not that it's just that's how it is normally, and then on every other day, which is most of the days, the conditions are right that you get the sinking effect.
Well, because we've just demonstrated that refraction will loom something up.
Yeah, and I've just we've been
And
through it.
again, the
sinking will
quantification
happen on a flat plane too.
the quantification of refraction has been done. We can model it out exactly as it should be. Let me get up Mick West's thing.
Yeah, but what I'm saying here is that you brought up the Chicago skyline, and you're presuming that you're starting off from something behind the curve and then it's looming up. What happens if you turn it the other way around and presume that, okay, you can always see it, but then you've got the atmosphere to contend with that lowers things due to sinking effect?
Right.
Huh?
Because we've quantified what refraction does, and we know how it will act based on a temperature profile. Now, this is a refraction simulator that Mick West has written based on the known quantification of refraction. And it shows that you can just move these about, and actually it shows you if the temperature profile is different, what you would see. And you don't have to have much of a difference in temperature for the skyline to actually be visible. But then, let me get rid of it.
Can you show me how he came to this conclusion? How he made this actual graph and this index of refraction? Can you show me the experiments that he performed, the tests that he performed?
Well, he would have gone on the quantification and stuff that Gauss did, for instance, using theodolites. My mouth is not working. That word that I apparently can't say right now.
But theodolites aren't measuring the temperature and they aren't measuring the air pressure. Theodolites aren't doing that. Theodolites are just observation.
Yeah, but what he managed to do with them by having two at different points and knowing what the horizontal for him was, and taking measurements of temperatures on certain days, he was able to say,
presuppose a globe and engineer it.
Nothing presupposing. He's saying, okay, well, let's do this measurement, and we can see that on this day the temperature is this, and we have to adjust the theodolites at this amount so that they can see each other, and then that works with the math. The refraction could work like that. And it's not presupposing anything. It's taking a temperature at certain points and knowing that then the refraction would work like that.
I want to, like I say, I'm going to ask again for the evidence of all this, where you actually got this to make this index of refraction. Not theodolites, but I want to see the temperature gradients, the pressure gradients. And then I also want to see that if you can apply the same logic to a flat plane and apply the way that things would happen, because I am sure that you would also get a
look. Where is it? We've actually got a flat plane observation in here.
You've also got it on
the same. I guess could be asked of you, Ranty. But Ranty, you could also ask the same of you. How are you making all these assumptions?
No, this is your proof. This is your proof.
things are
You're
not.
saying that
No, but okay. So
these are your proofs.
it's not proof.
You're saying
It's
behind,
not proof.
You're saying this is
It's
behind the
evidence.
curve right
It's
now.
evidence
there we
to
go.
support. Well,
No,
hold on. Hear me out. It's evidence to support. But what I'm saying is, you keep saying, "Oh man, all these other guys. How did they get this? How did they come up with these answers?" Well, how do you come up with your answers when you say, "Well, things are looming and things are being refracted, and this is why we're not seeing the boats go off into obscurity as a little dot. We're actually seeing them go over the horizon from the bottom first, and it's an optical illusion." Guys, that's all it is. You say that, and then you say we should be able to provide the proof as to why we believe that refraction exists, but then you don't have to provide the proof as to why you think looming exists, or why you think that these boats aren't just disappearing as dots. They're going. Well, whatever.
I don't think
your beliefs that you. But okay, so when you
Looming's
see a
your-
ship going over the horizon, but okay, no, I don't talk on those terms with all of that. Okay, I stay away from observations like yours because they're ill prepared. You don't ever put forth data. You show one portion of data, which is the observation. That's all you show, and you try to derive a conclusion from your observation. You came to the conclusion that the Earth is flat using your observations. Is that not correct? Or did you just believe what Anthony Riley said?
Why would you bring Anthony Riley into this, and as if that would have any
No,
effect
okay,
on
whoever. No, okay, no. Okay, pick a flat earther and insert the name there. Did you believe it because they told you, or do you believe that the Earth is flat because you've gone out and done your own observations?
I've gone out, I've done my own observations, and I have
Okay, so
approximately
your
6
observations,
terabytes.
Ranty,
Hold on. I have
but
about 6
your
terabytes
observations
of data,
are not complete.
and they are. In fact,
Go
probably,
ahead.
I would say
No, they're
probably
not.
a third of my observations I have done extensive research on with plenty of
Okay, where are your control
imagery.
measurements in any of your observations? Where are your control
You
measurements
can't,
in any of your observations so that somebody
you
could go
cannot.
out and reproduce your experiment?
Yeah, so you cannot, I cannot anyway, I don't have the ability to go and test the air temperature across the entire gradient for everything that I'm
Right.
trying to film. So I
So the
cannot do that.
conclusion you came to was
But what I
based
can
on
say
a
is-
poorly formed set of data.
No. I've seen inferior
Yes.
mirages. I've seen,
Uh-huh.
what would you say in inferior mirages? Is that the Earth curve, or was it an optical blockage?
An inferior mirage. Well, all mirages are forms of refraction. They all when someone says forms of refraction, that's just explaining what refraction does under certain atmospheric conditions. An inferior mirage is just a type of refraction that I believe the inferior mirage is when things get lifted up into the air. Is this not correct? That's due to temperature inversion.
An inferior mirage is what? Man, do you even
I'm
know what
asking.
you're doing? An inferior mirage is
yeah, I do.
Go on. I
Yeah,
want
go
to see
ahead.
what you said. Go on. Tell me what it is.
Did I not just ask you if that was? I just
No,
did.
I wanted
Didn't
to
I?
hear
And
what
I
you
asked
said.
you, was that
I wanted
not
to hear what you
right?
said. I'm sorry, but I want to see what you
Pay
what you
fucking
say.
attention, right? Pay fucking attention.
Go ahead.
No, you
Go
pay
ahead.
fucking
Go ahead.
attention. I just said it.
Right.
Go on.
So
I'm sure the chat will tell you.
okay,
I'm sure the chat will tell you.
this is what an inferior mirage is, and it's caused by a temperature inversion. So that's what Team was trying to say. This is an observation of a simulation of what you would get with a temperature inversion. As you can see, the temperature drops instead of rising, but then starts to rise, and that would cause this refractive effect that you see here. You can move these about to show how it would change if you had even more weird effects. But an inferior mirage is caused by a temperature inversion in the gradient.
So that's what Rumpus would say, yeah. Well,
I imagine. I mean, I'm not Rumpus, and he has a different knowledge set to me. So, I don't like to go on what other people have said unless I'm speaking to an expert like Dr. Young, who is literally one of the world's leading experts in refraction, and Mick West, who has done the physics and simulated the physics based on known quantification of refraction. These are the people that I would refer
I
to.
believe what I'm explaining is a superior mirage, which is where things appear to be lifted up beyond the horizon. Is that not what you were talking about, was something being lifted up beyond the horizon?
Yeah, so here's a superior mirage. But I think Ranty's
That's what
just
we've been
talking.
pretty much talking about the whole time. He asked about an inferior mirage, which is that's where you see an inferior mirage would be kind of like where you see that maybe where you, like an oasis, like in the desert, right? Is an inferior mirage like what you would see in a desert, right?
I'm presenting
like
right
where
now.
It looks like there's mirage. Fucking.
Yeah. Right, so there you go. So you're getting that inferior mirage. You're getting that bit where it looks like it's floating, right?
Yeah. So
which is what we see
here.
What
I fucking said.
Which is what we see here, right? So these things in the distance look like they look like they're floating, right?
So let me
temperature inversion.
Okay, so let me ask you this, right? So
well, let me ask you, is that not what I fucking said, Ranty? No, hey, Ranty, is that what I fucking said?
No.
Jesus Christ.
It isn't what you said.
Right. Trying to be nice to you, dipshit.
Come on.
So, from the same observation point, same height, same tide height, same weather conditions, we just have two different images that are resulted in this mast in the distance. On the lower image, we can see shore to shore, we can see a truck in the bottom here. Obviously, we can't see anything when there's an inferior mirage there, there's blockage. That's my point.
Right. When you say blockage, do you just mean that we can't see it?
Well, yeah, you can't see it.
Yeah, I mean that's you're right. It appears the island appears to be floating, right?
It does when there's an inferior mirage, but it's not floating.
No,
it's
not,
really there.
Yeah, of course it is. And
it's the inferior mirage, the overlap blocks off what you can't see from the bottom.
Yeah. In this simulation, these triangles you can see on the top that they go off into the same, but they're all the same, right? They go off into the distance, but they're all the same triangles. The further away you get, because of the inversion of the temperature above the water, around about here, it could be a low pressure system.
Are you presenting something? Right. Sorry.
Yeah. Do you not see it on the screen there?
Yeah, I was presenting. I was.
Oh, all right. Sorry. Yeah. No, go back to the vMix call. Sorry.
Yeah, go on.
Right. So these triangles are these pillars here, right? And as you go into the distance, around about here, there would be an inversion of the temperature, which is represented here, where the temperature above the water has dropped dramatically, and then it starts to rise as you go up, as you would expect. It could be because of a cold weather system pulling, low pressure system pulling out or something, but it's easily explained by our knowledge of refraction, and you don't have to have that dramatic a change in the norm to get these effects. I mean, my point is that it's all explained on the globe with our knowledge of refraction and our knowledge of the shape of the Earth, and we never have to presuppose the shape. We never have to. I never presuppose the shape or the dimensions of the Earth because it's been measured. I've got references I can refer to show that the shape and size of the Earth has been measured. So I never presuppose anything. I just go on measurements and stuff that have been taken previously.
Okay, so can you pop me back on again? Because I've got a couple of questions to ask you on this. This is real life image. It's
Let me just one sec. There we go.
So these are sort of real life image taken two separate videos. I actually put the videos out side by side on a video to prove my location, to prove the tide times and everything. You can see that everything is that. On this day, would you say that this is just a very clear image on the bottom?
Yeah, I'd say that's a relatively clear day. I mean, I'd say looking at the water, it's probably sea state 1. It's not that choppy. You can pretty much see the shoreline. I'm not entirely sure if you can see it. I don't know that particular location, but you can see what appears to be the shoreline and what appears to be a van or a car. So it's pretty clear to me.
See, in your model, that's looming.
Yes. Well,
I shouldn't see that.
I mean, looming isn't the entire explanation. There's a lot more
No.
going on than just saying the word looming. Looming is
Well, there should have been,
a colloquial description of an
there should have
effect
been,
that we see.
well, there should have been 35 foot of blockage between myself and the shoreline of that observation.
And what's the distance there?
It's about 14 miles, I think. Top of my
14
head, you know, you caught me
14
off
No, all right. So
guard here.
let's just say 14 miles. So it's 1 degree for every 69 miles. So we're looking at roughly a quarter of that. So light would have to bend by about 0.2 degrees.
Yeah, but my point that I was trying to make is that the clear image, the shore-to-shore observation with the truck,
Yeah.
right? There should have been 35 foot of obstruction between myself and that, which coincidentally would have matched the inferior mirage at the top. This inferior mirage, put a line through the center of that, so basically down just beneath this mast here. That would have been give or take a foot or two, 35 foot down to the shoreline. I've actually been to this location. And what we're seeing here, as I say, is everything beneath this cursor now shouldn't have been seen. But to me, it's just a very clear image on a very nice day of a shore-to-shore observation. Yet the one that matches the globe is this one with the inferior mirage.
Well, the thing is, they both match our model. They don't match the geometric shape because we never see the geometric horizon. We always see a distorted image of whatever we're looking at. So both of those images can work in our model based on our knowledge and our quantification of refraction. The top one obviously has an inferior mirage. I'd say there's obviously an area above that water where it's got particularly cold and it's caused a temperature inversion to create that, to give you a lapse rate that is a lot deeper to create the coefficient of refraction that gives you that inferior mirage. But neither of those are an issue on the globe. Like I said, if that's about 14 miles, to see that clear image, it means that light only has to bend about 0.2 degrees, which, when you take standard refraction, is a lot more than that.
But like I say, what you're doing now is you're automatically going to this idea that you're having to curve light. Take it from my position, which would be, I just see it. It's a very nice observation. I'm just seeing shore to shore. I don't need any bendy line.
It's a very nice observation, but
I don't need any bendy. Just let me finish. I don't need any bendy line to see that. I just see it. And yeah, on this one, I just have an inferior mirage, which is blockage. It's causing me to not see it on this day because, for whatever reason, you can definitely see that this inferior mirage is hiding everything that I was able to see on a clear day. Now, if you know anything about observations over water, apart from days when you've got the water splashing quite close to the shoreline, once you go past 8 or 10 miles away and you can see things at 8 or 10 miles away, you always get an inferior mirage. You always get an inferior mirage. It doesn't matter how many times you film it, you will always see an inferior mirage. End of story, period. That's it. You will always get one. And this is...
Are you saying you will always get an inferior mirage when doing observations over water?
When you can see more than, if you're anything below, say, 20 feet in observational height, and once you get to around about 10 miles and beyond, then everything at least at that observational height starts to go into an inferior mirage, provided you can see a boat at that distance. You know, so the boat, for instance, the observation that we were talking about before, where you see a boat going over the curve, that's not the case. You see this inferior mirage of the boat. In fact, this is a very good image to show that, is that if you imagine that this image on the bottom is the boat, and that's, like, say, a mast on the boat, as the boat disappears into the distance, the bottom of it gets hidden behind this inferior mirage, and it's very clear in the footage, very clear. If you take screenshots throughout that video, you will be able to see it yourself, and you'll see that mirror image underneath it doing exactly the same as this, which is hiding it from the bottom up. And this is demonstrated on... I've got a video I want to show you guys. Let me pull... Oh.
Yeah, but my point is that none of this is not possible on the globe. I mean, That's the issue that I have. The observations that you're showing,
Okay.
it's not something that is an issue in our model.
Can I step in for a second? Can I step in for a second? Ranty, you said at the water level, when you get really close to water, right? You said that there's always an inferior mirage, correct?
Yeah, unless you've got a wave that's in the foreground that stops you from seeing.
Yeah, I'm not talking about. Yeah, I'm talking about ideal situations. Yeah, we'll say an ideal situation where the wave or the ocean is perfectly still. It's pretty much just like a mirror that we're looking over. Okay, you'll agree that even if you took an observation on that day, the closer you got to the surface of the water, you would get an inferior mirage, correct?
Probably on those particular days. The only times that I've ever seen absolute still water, we've seen pretty much shore to shore.
I'm really saying still water, so that way there's no obstructions. You know what I'm saying? That's the only reason I'm saying still water. I'm just basically saying that it is your contention that if we make these observations at or near the surface of water, we're always going to get an inferior mirage. That's what you just told Fight the Flat Earth. I'm just verifying that again with you. Is that correct?
I mean, I would say at least 97.5%.
Do you understand why?
Yes. Well, you're going to claim.
I'll agree with you on that. Do you understand why?
Go ahead. You tell me.
I just asked you, do you understand why? Because
Well,
that's
I
a
know what
claim
you're
that you're
going to say.
making. Okay, you need to be able
It's
to.
a claim that
what am I going to say?
It's not just a claim that I'm making. I've done probably more videos than the whole globe Earth has put together. I've got so much data.
I'm sure you have. We don't need to do videos. We have yours. What are you talking about? So what I'm saying is do you understand why at the water level? Hold on, Ranty. If you don't understand, I'll explain it to you. Okay. What do you think happens when you take at the surface of the water? When you have water vapor, a lot of water vapor in the atmosphere at the surface of the water. You would agree with that, right? That the highest concentration of water vapor in the atmosphere is going to be over the ocean at the surface.
Yep.
It's going to dissipate as it goes higher into the air, correct? Okay.
Yep.
Now, when that happens, when you get into that zone where you're looking through primarily a majority of water vapor relative to any other position in the atmosphere, you do understand that looking through water vapor is going to give you less of a refractive index, not more.
Right. So what are you going to say?
It's going to reduce the density. It's going to reduce the density of the water. It creates a greater density above that area of atmosphere. So when the light ray leaves the person or leaves the object and is supposed to go directly into the water, it enters into that band and is bent upwards. That's an inferior mirage. And it's going to happen as you get closer and closer to the surface of water. That doesn't prove anything. That's why you have to be wary of observations that you take when you put your camera or your observer into that band of the atmosphere. When you put it into a band, when you're looking through the band of the atmosphere that's directly over water, you're going to have less dense air. That's going to cause the light to bend up because it's going to bend towards the more dense air where there's less water vapor, and it's going to bend up that way. That's what causes the inferior mirage over water. So using that, if you don't know why you're using that, you're just using that and saying that, well, there's a scientific explanation as to why that occurs. You would need to explain now why we can use that to prove that it's a flat Earth, and we just have to disregard all the refractive properties of the atmosphere directly over the surface of the water.
Okay, so am I still presenting?
Let me get you back up one sec. Yep, there you go.
So this is done in miniature. So this is a miniature RC boat on a lake. The lake itself is only 600 feet across. That's the total length from one side to the other. It can only go as far as 600 feet. The center of the lens is to 1.5 inches off the water. Now, at no point should there be any earth curve between ourselves and the boat that we're trying to see. There should be no obstruction, physical obstruction of earth curve between ourselves and the boat. Let me just show you this boat. Here it is. This is what it looks like on the water. This is obviously it moving around. You can see an inferior mirage already. You can see it here, and you can see the background as well. Can you see this inferior mirage of the background? Yeah, and you can see the boat as well. It's got an inferior mirage on it too. We're just going to play the video in a minute. You'll just see the boat completely disappear. It vanishes. Now this boat is, I think it's 3.5 inches high, and we lose all of it. It disappears completely. Now, as I say, there is no earth curve between ourselves and this boat, and it's a very still, calm day. But the boat just disappears into the inferior mirage and vanishes. It's gone. Okay, so there it is. It's pretty much gone there. There we go. Now it has gone. If I scroll a little bit further to 3:15, you'll see the lady. She picks up the boat. Now let's put it from here. She'll pick up. She's got it in her hand, and she's going to put it into the water. Here we go. She's got it in her hand. She's going to place it into the water. There we go. She's just placing it into the water now, and you can't see it. There's the inferior mirage. You can see the repeat of her legs. There's the inferior mirage going through here. She's just placed the boat down here, and it's not seen. It's not visible. You should be able to see it on any model. Doesn't matter whether you use a globe Earth or a flat Earth. You should be able to see that. So what's obstructing that? What's causing that to disappear?
Yeah, why should you be able to see that? If you
why can't we see it on any model? Why can't we see it? What's causing what is
refraction?
It?
Refraction is causing.
Yeah, but it's causing what? It's causing the sinking effect. Yeah.
Well, it's causing all. I mean, we're seeing a whole bunch of effects there.
Yeah. So this downward.
That's why I was saying when you take your observation next to the surface of the water, you're going to get a different refractive effect than you will at 6 feet above the water, or 12 feet above the water, or 18 feet above the water. That's why your observations, when you want to prove something, you can't go to this one little specific. That's called the Texas sharpshooter fallacy, by the way. When you go to one specific set of data and say, ooh, I'm just going to use this one specific set of data to prove that what I'm saying is correct. Well, when you do the same observations at higher and higher elevations, you start to see that the original conclusion that you can draw from your first set of observations does not fit the set of data that you're taking with your second and third and fourth observations.
Well, what we're seeing here is we're seeing the light bending down. It doesn't matter on which model you use it, it's hiding that boat. That light has never reached the observer, right? Whatever light is coming from that boat has not reached the observer. It's gone somewhere, right? But it certainly hasn't gone to the camera.
The light is being bent up. When you take it down like that, the light's being bent up relative to you. It's going through that layer of less dense air, which has more water vapor in it, and it's being bent up into the more dense layer of air, which is how refraction works, which is an inferior mirage. That's why you don't see it when you take the camera down there. Any light that would be any light that could make it to you would be bent upwards.
Right. So when you're trying to see, let's say, some distant land masses in the distance, and you're at an observation height of 500 feet, eventually you're still going to get into that very narrow band, that very narrow angle, because that's what will happen. You'll have a shallow angle at, let's say, 50 miles, and you're at 500 feet. You're going to have a very shallow angle. It's going to be comparable to this kind of observation. It will hide the entire mountain that you're trying to look at.
No, but okay, Ranty, this is where you're going backwards from your observation. You're thinking from you, because to you, you're looking out and seeing the top of the mountain close to the horizon. When actually that top of the mountain, if you're at 500 feet elevation, the top of the mountain, if you drew a straight ray from the top of the mountain to your eye, it would never really get close to the surface. It appears to you to get close to the surface because the place where it would cross the geometric or the visible horizon, to you, the angular distance between the horizon and the ray that you're using to trace out the ray of light to the object, to you it only has a small angular size between the horizon and where that ray is. But in reality, if you were to go to that section, the distance between, let's say you were looking at a mountain that was 1,500 meters from a observation point of 200 meters. Well, to you, like in elevation, to you, it would appear as that line got close to the horizon because you're far away from the horizon. But in reality, that line doesn't come close to the horizon. It's a kilometer up, 700 meters up. I mean, it's a good distance. It's not at the surface, which is what we need to avoid when we're trying to use evidence-based observations.
So this is essentially what you drew before in Paint. This is pretty much the same with the density gradient.
Back up 1 sec. Okay.
So this is essentially what you drew when you were trying to explain it on a globe. I'm trying to show this on a flat plane, and the reason I've done that is I've had other globers included. As I say, I've had the Rumpus, Stingray, McToon, all agree that this will happen. Is that the light ray, let's say, that's in the band of the green, that's trying to get to you over in the red, that light ray will have to travel down through these gradients. Right, so
yes.
This is... So if we're... So I've got another guy over here, so he's trying to see this tower over here, right? And he's going to have to be looking through these gradients of light, these gradients here. Let's go to the next. So this is light. This is how the rays have got to go from him. So it's going to set off straight, like you said. Then it's going to have to go through the gradients to get to the eye of the observer. Correct?
Mm-hmm.
Yeah, I don't think anyone's denying that.
Right. Okay. So So that's good. Let's go on to the next one. Come on. So here we go. So now look what happens when we look at the bottom part of the tower. So as the bottom part of the tower goes through, it comes through the gradients, and it doesn't kind of reach the observer there.
Well,
Can't make it out.
Okay.
Can't make it out.
But the issue is the light isn't just going to automatically go down. That line that you've got that is equal to his head height would just go in a straight line.
Which this one here?
Yeah. Well, let's pick a point that's equal to that guy's head height.
Oh right. Well, obviously somewhere down here. Yeah.
Yeah. So that light, it doesn't have to go down to meet his eyes. So he would just be seeing light, directly in a straight line through what would be no gradient.
Yeah, a good way to explain this fight is to say that, Ranty, in this observation, Ranty, give me 1 second. I just want to point something out. In this observation, if you took go back to that picture, please, so that I can kind of refer to the picture as I'm talking. Fight. I don't know if that was you or that one, please. Okay, so if you were to imagine the observer height on the tower, okay, like not the top of the tower, but where the head level is, the eye level is. But imagine that on the tower. If you draw a straight line between the tower and the observer, it would stay in the same band of gradient the entire way through. It would be no refraction whatsoever. It would just go straight from observer to the person. That's it. Now, everything above that would be distorted because the top of it would have to travel through different gradients. The middle top would have to travel through less different gradients. As you get closer and closer to the middle, it would get less and less distorted because it would have to travel through less and less gradients to get to the observer. So that's what we're saying, is that you would still see what's directly in front of you. The eye level should not be any different. Under ideal circumstances, of course. If it's if you have if you're looking over long distances and there's a lake in the middle of it, well then you're going to have slightly different atmospheric conditions over the lake. But let's say in an ideal situation where the atmosphere is simply, the way we see it in reality, a gradient, and it forms perfect bands. Well, that view should not be obstructed. There should be no curvature of light whatsoever because it never enters into a different density of atmosphere.
Okay, so here we have the same mountain range in the distance from different observational heights. Yeah?
Mm-hmm. Yeah.
So the lower image is from lower down. That's from higher up. The top image. Yeah. So scaled to height. Look at the drag and the stretch and the warping.
Now there's a reason for that, right? The lower image is taken when you're closer to the water, right? Mm-hmm. That means that
same as this.
Yeah. So that means that observation has a higher lapse rate. There is going to be a greater change in temperature per meter than at the higher elevation, because the temperature changes more rapidly the closer you are to the water, which means that you will get more refractive effects when you are closer to the water. So you are going to see all stretching, towering, looming, anything when you're closer to the water, because that is where you have the higher lapse rate. The further you get away from the water, the bigger the distance is for the same amount of change in temperature.
So what we're looking at here across this band here is this dynamic area. There's a dynamic area just above the water, yeah, for the observer, right? This is a dynamic area. There's a lot of things changing. There's wind that will be blowing across the ocean. There's swell. You'll have some kind of swell. You'll have chop. You'll have evaporation. There's all this stuff going on down at the bottom, which is, you know, as was explained to before about these particulates that would be in the air, will cause blockage of the light. The light won't just be able to go in a straight line to the observer. It won't be able to do that simply at these low observations. And I've also had the rumpus on my show. I've had Stingray on my show who modelled this out, modelled this exact thing out on a flat plane, and it disappeared from the bottom up. He modelled it on my show. So it disappeared from the bottom up. The light never reached the observer. I've had the rumpus on the show. I've got the videos ready to play. Now.
And again, it would depend on the conditions above the water.
The observer.
So even assuming this is a flat plane, okay, in perfect conditions, your eye level isn't going to be refracted. But if there is some temperature inversion going on, if there's some wind, some breezes that are changing the temperature as you look through, then there's going to still be refractive issues. But to make those models, we would have to know, or at least guess, what the temperatures at certain points were.
Yeah, and exactly this is my point. Because if you look at Red Pill Philosophies' shore-to-shore observation, my shore-to-shore observation...
Sorry, you mean Mario?
Who?
Luigi.
No, I'm pretty sure he's Mario. Maybe he's even Wario. Sorry, well, it's the moustache.
Oh my god.
So, Red Pill Philosophy, myself, other people that have done shore-to-shore observations, they always happen when the water is almost still with barely a ripple across it, where the conditions are very nice, there's no wind, anything like that. So it's a pretty settled it's a pretty settled conditions. So that in that particular case, you would get the light ray traveling to your eye.
If the Earth was...
May I present something?
Drops again.
No, we're here. Can you hear us? Ranty, you there? I can hear him. Hello?
I can hear him too. Make sure you don't have us muted going to him.
No, he should be able to hear us. I think he's coming back.
Did he freeze, or is he just... Okay.
Oh no, he did drop out of the call, the VMix call. He should just be coming back.
All right, I have an observation from Tommy Gronvold I want to show. Because he sent this to me just now. He took it, so there shouldn't be any... There shouldn't be any like NASA claims or anything like this. There's no distortion or anything like that in it. But we'll look at them real quick. Just loading them up while we wait on Ranty.
Yeah, let me just email them quickly.
I'm trying to be nice, fight.
I know, it can get hard.
He's not actually being very like bad or anything. Like,
hello.
Like, it's not
hello, there he is. He's come back. Don't know what happened there, but you're back anyway. Right.
It's this thing.
It's internet.
Yeah, I'm having issues with it.
Right. So, team has some observations from Tommy Gronveld. He wanted to show you quickly, if that's okay.
Sure. Just one thing though. I just wanted to clear up that final point, which was that when you look at Red Pill Philosophies, my videos, where we see shore to shore, you have these very still atmospheres, the still water. You are able to see through, exactly as Team Skeptic has just said, this is what you'd expect to see, so you'd see shore to shore. But it's very rare that you get those conditions. So what you're going to get is you're going to get a lot of mixture and turbulence at the bottom. Those light rays would never reach you and things would disappear from the bottom up. And it's been modelled out by your fellow globe earthers.
Well, Ranty, on the globe Earth, we never get that situation. That's the thing. A site-to-site, 6 foot to 6 foot observation, let's say over at least some kind of distance, 1 mile, let's say, we're always going to be looking through gradients of atmosphere, because on the globe Earth we could never have a line of sight that was direct, you know, having 90-degree zenith angles, let's say on two theodolites, you know what I'm saying? They would always have a greater than 90-degree angle when looking directly at one another. So we never
Yeah,
get
so that's what
that
I'm saying.
situation looking.
Yeah, but isn't that the case?
No,
isn't
yeah,
that the
that's
case though?
that's what we're saying. When you see that, but when you
Because
see
you're
that, you're actually
presupposing a
seeing
globe.
refraction.
No, again,
No,
we don't.
'cause you're
We don't. We
presupposing
don't
a
have to.
globe.
We don't have to presuppose because we've got measurements to go on. So we never presuppose.
What
a globe.
measurements?
I
What
mean, there's-
measurements do you have?
I've got loads. Give me a sec. I'll bring up a list of them.
Yeah, I want measurements, proof. Show me.
Display this. Let me display this because it has to do directly with what you were saying. With the clear water and all this. Let me just show you, and I'll let you get a chance to respond to this. This comes from Tommy Gronvold in the chat right now. He also is a great content creator. So you guys out there looking for somebody who's doing experiments just like Ranty does, go ahead and check out Tommy Gronvold. All right. So in this is just the model of what we're going to be looking at. He took one observation from one side at about 70 foot observer height. He uses a basic, water level to make sure that he's looking at eye level, that his camera is perfectly level. But here's the first picture right here, and then that's just, like I said, the basic setup. Here's to show that he used, that basically a tube level. I don't know what you would call
Team,
that.
are you presenting that?
He's good.
Yeah, I'm not. I'm just seeing the one image.
I'm presenting it. Yeah, well, you know how we have a vMix. I have a second
Yeah.
image up there, and I thought it was up. My bad. Okay, so this is just to show you that, how he determined that he was at eye level. Here's the observation that he made, just so you can see that his camera is at eye level to the water in the tubes. The only reason I'm explaining this is for the people in the audience, Ranty. I know you get the general concept of what's going on. Let me jump in. Here's the last picture right here. Okay. So as you can see, let me jump between these two pictures. You can see where the line generally crosses the tower in the distance, correct?
Mm-hmm.
Okay.
I do, yeah.
And then this is, let me go back to let me go to the other picture. Okay, so that's where the line crosses the tower right there. It's about 70 foot. However, measured, this is about 1,000 foot tall.
What's about 1,000
in
foot
reality?
tall?
The tower. Let me
tower's
pull
1,000
up
foot
Tommy's
tall.
messages to me. No, let me say the turbines. I'm sorry, the turbines in the distance, not the tower. The turbines in the distance.
1,000 foot tall turbines? Where in the world are they? I think the biggest ones in the world are only 650 feet.
Hold on. He's the one that took the observation. He's sending them to me right now. So let me see. He's showing some other pictures about his actual data in case you wanted it.
Okay.
Let me ask Tommy before I just try to speak for him. Let me wait. I'm sure he'll be responding in the chat, so I'll watch chat real quick and see what his response is. Actually, Tommy, if you'll respond to me on Discord, it'd be a lot easier.
But in answer to your question about measurements, there is a whole list of measurements that have been done over throughout many years, repeated many times. One of my favorite ones to go to is the triangulation of where is it? Here we go. The transcontinental triangulation of the Americas.
Okay.
Where
they're I'm sorry. He said they're 1,000 feet in elevation at the top of them because they sit on a 500-foot hill, a 500-foot hill. That's why it's 1,000 feet to the top of the turbines. I don't like putting out other people's stuff because I wasn't there and I don't know how to properly answer for them. So forgive me for having a delay in answering the questions for you, but I got to wait on Tommy to respond, and there's a slight delay with the stream. So,
but this is just one of them where they accurately measured it based on many different measurements over many years. I'm trying to get to the tables. Actual surveying work across like a good portion of the world, And the list that I just pulled this from, there's different ones from all over the world, and they accurately measured the radius of the Earth many times. Let me just go back. So there's actually a whole bunch that I can give you on this list that you can look at yourself. You've got the account of measurement of 2 sections of the Meridional arc of India. You've got the transcontinental triangulation of the America arc of the parallel. There's loads. So I don't have to presuppose a globe. We've got actual measurements of the shape of the Earth. So when flat earthers say, well, you just have to presuppose a globe for that to work, I don't ever presuppose a globe. I go on accepted measurements that are easily available to anyone. If anyone wants to check this out, it's mctoon.net/r. There's a whole list of measurements of the shape of the Earth, and even some history of the determination of the figure of Earth from arc measurements. mctoon's done a great job with that. But yeah, so I never have to presuppose a globe, Ranty. Do you accept that I don't presuppose, I go on measurements?
I don't believe the measurements are accurate, so we're going to disagree on that.
What would you have to say that, though? Because these are from people whose jobs it was to survey the land that they were on. This is from professionals whose entire job was literally to measure the Earth, and their expertise is what I would go with in this case. What do you have to say that these measurements are not right?
What's the name of the file, and where can I find this information?
mctoon.net/r.
Right. Okay. I'll
and like I said, there's about 12 different surveying measurements of the shape of the Earth. So again, surveyors whose job it is to literally survey the world, survey the Earth, and they are the ones that came up with the conclusion of this shape, and it's their measurements that I would refer to. So I don't presuppose a globe, and I really don't like it when flat earthers just say to me, well, you're just presupposing a globe, because I'm not. I'm going on measurements.
Well, you're taking somebody else's measurements for it, firstly.
That doesn't
and
matter.
Presuming that they're correct.
That's fine.
Well, it does.
No, it really doesn't, because not everybody has to do every individual measurement themselves. We rely
well, then you take
on
it on faith.
Well, it's not faith.
Yeah, you take it on faith.
It's a logical assumption that they know what they're talking about, considering they were experts in their field. And when you have, say, I think 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I think there's 11 things there from different groups around the world that all give the same conclusion. I'm not just going on what one person has said. I'm going on individual people, different people that have all said the same thing based on their own empirical measurements. So I don't have to presuppose anything. I don't have to presuppose that they're telling the truth, because they have peer review in the other people doing it to back up what they've said.
Can you present my screen?
Yep, one sec. Let me just get that up.
So, Team Skeptic, you presented an image before and you asked me about these turbines in the distance. Would you agree that turbines in the distance appeared to get smaller?
Team, you there?
I'm sorry. I'm sorry. I had my mic muted. Yes, there can be atmospheric conditions that cause stretching and magnification, but like if we said in an ideal situation, yes. As the turbines got away, they should get smaller in angular size. Correct.
And there's a formula for that as well. Do you know what the formula for calculating angular size and stuff is?
I'm presenting an image. If you want to have a look at this, Team Skeptic. If you could. Okay, so essentially these are all the same turbines, but they're obviously getting further away. They're getting smaller. Where would you say the center of the frame should be if I was looking at this turbine here in the foreground? I mean, where do you think would be the parallel for this? If I could just keep going down, you tell me when to stop.
Well, hold on. I'm not quite sure what you're asking me. Are you talking about where?
Okay, so if I try to,
like where eye level would be?
Yeah, eye level. About here, maybe,
I
where my
would.
cursor is.
I mean, that's if the camera was perfectly straight to
I'd say a little higher than
90
that.
degrees to the pull of gravity. Yeah, I would say it would
Maybe
be
there.
Yeah,
dead center of the frame. Yeah, dead center of the frame.
Yeah.
Possibly a little
So-
higher, even maybe.
So in the background, we have a turbine that's the same height as this one in the foreground, and yet that turbine is below where you said the camera height would be in the center of frame, which would be here. If you put a straight line across that, you'll see that that turbine falls below that point. Its angular size is reduced in size so much that it is now below the center of the camera.
Yeah, but we don't know if the camera
Yeah,
is the
I
same
don't-
elevation of those stuff, and to
Oh, no,
calculate.
I wasn't trying to trick you. I was
No,
just
I
asking
know.
a question where you
No,
thought
I'm
the
not saying
center
you
of the
are. I'm
frame
not
would
saying
be.
you are. But
And
well,
I'm demonstrating
I'm
that
picking
when
the
things
center
get
of
smaller,
the-
they
well, I'm
end
picking-
up getting lower.
Okay, well, I was making several assumptions here, like that we're looking at the whole picture, that the camera was perfectly level to, to the pull of gravity, or to whatever you want to believe that the downward accelerating force is. I'm assuming all of that is correct, and if any of that is not 100% correct, you're going to get something different than what you or I could predict or believe.
So you would think that this
Like
isn't
if the
just a
camera was
normal
tilted
representation.
just 1 degree. Well, I don't know.
You just don't think that this is a normal representation of what you'd expect to see? Because this is what I see all the time. I film these turbines all the time. You see the same effect. Things get smaller with
No,
distance.
I don't.
Well, yeah, of course things get smaller with distance.
I agree with that.
There is a formula to figure that out. Under perfect conditions, you can use the alpha equals 2 times the arctan of g over 2r to calculate the actual size of how things should be based on how far away they are. But of course, we have an atmosphere, so that everything's always going to be distorted to some degree.
So in this case, it's being distorted that it's sunk beneath the center of the frame.
Well, again, I don't know the height of the. I don't know the height of the camera, and to compare it to anything.
Nor do I, because I didn't take the image. I'm just asking. It's literally a thought process between the three of us to ask you. Looking at this image.
No, that's what I was saying. Right?
If I make the
Okay,
assumption
go ahead,
that the camera height is halfway up that first turbine that we see, right? If I make that assumption, then yeah, it appears that it has fallen below that. But I have to make an assumption to be able to even make that thought process. And I'm not saying that there is effects of refraction that cannot make things sink. I've never said that. But the effects of refraction are known. They have been quantified. We can model them out. If we know the temperature profile, we can model to see exactly what we should be able to see even with the atmosphere there. But we have to know the temperature profile.
So assumptions are bad.
Hey, Fight, do you happen to have that? Ranty, have you sent that image to Fight? If not, will you please send that to him? And Fight, will you send that to me real quick?
Yeah.
What, this image?
Yeah, would you mind just emailing
wanna
that to
see
me,
something.
please?
Yeah, that image, please.
Yeah, I'll email it you now. 1 second.
But yeah, assumptions are bad. As I was taught in the military, assumptions make an ass out of you and me. So yeah, that's why I don't make assumptions. I never make assumptions or when I'm coming to a conclusion. I look at the evidence and reach a logical conclusion based on that.
There you go. I've just sent it to you now, so you should be receiving that any second now.
Okay, I think I've got that. Yeah.
Whilst we're on this, can I do another thought process with you guys?
Go ahead, please.
Okay, so I took this image in the center, so I'm still sharing screen, Jeff.
1 sec, I'm just passing that image to Team, and then I'll get your screen back up. There you go, Team. I've just sent that to you on Discord, bud.
All right, thank you.
And now get back up for that. Okay, you're presenting again.
So I took this image of these wind turbines not far from me. They're about 13 miles away. and one of your Glober friends, actually modelled it out for me, both on a globe and a flat plane. It was Sean Hufford, so he actually modelled this for me. Well, actually for himself, but he modelled it, and I snapped these shots. So he took this image. He worked out that I told him the distances between each turbine, how far away they were, and what my observation height was, and he modelled them out. So there's one on the left that's a model, and there's one on the right that's a model as it would look through the camera. So can you guess which one of these two is modelled on a flat plane and which one is modelled on a globe?
No, not just by looking at them, I can't.
Could you, Team Skeptic?
I'm not actually looking at that right this second. Give me 1 second to pull that up.
Obviously, the image in the center.
I was working with.
Yeah, the image in the center.
So the
is what
image
you're
in the
taking.
center is a real image. The modelling is scaled to height, distance, everything by Sean Hufford, who put all those details in his modelling software. And there's an image on the left and there's an image on the right, and one of them is a globe and one of them is the flat. Can you tell which is which?
No, but hold on. Can you hear? Okay, yeah. No, but I don't think you should be able to tell unless you. I mean, what's the distance between the two? Between the wind turbines?
I think it's from recollection. It's around about 0.7 of a mile. From recollection. Now, that could be wrong.
Between each of the turbines.
Okay, so
between each of the turbines, yeah.
Yeah, so we're looking at less than 1/69th of a degree between the two of them, and like whether they should be parallel to each other or, splayed apart ever so slightly, but less than 1/69th of a degree.
So
that
why
would be
when we
pretty
see
impossible
these sort of
for
images,
you and I to look at that picture and tell. Go ahead, I'm sorry.
Why when we see these sort of images, do we get globers saying that what you're seeing here is perfect proof of globe? It's like they can't process the idea that things get smaller with distance.
No, I don't think any
because you're not showing the bottom. You're not showing the bottom of the platforms or of the turbines. I'm sorry, following the curve of the Earth. You're not watching this. Like if you go and you look at Soundly's observations of Lake Pontchartrain of the causeway there, you can actually see the causeway following the curve of the Earth, and even though they get smaller, they appear to raise up in elevation, go over the horizon, and then begin to fall away.
So, which one would you go for? That was the question.
Honestly,
well, like I
honestly,
said, I could guess, but they would only be less than 1/69th of a degree difference from each other.
I mean, if you gave me 5 minutes, I'd be able to put
even
it
if I gave it wrong, yeah.
Well, I'll show you.
Even if I got it wrong, you're talking about one degree less of 1/69th of a degree in tilt would be the only thing different that you should see without seeing the bottom of the platforms.
But there you go. Once you show the bottoms, that's where it becomes.
See the bottoms.
Yeah, it becomes evident because you can see that against the curve of the Earth.
Exactly, but you can't see the bottoms on the real image.
Well, no, because there's refraction. That's the thing here, Randy. Everything you're saying.
People concentrate on this. No. People concentrate on things getting smaller with distance as being proof of earthquake.
No. I don't think anyone says that because things get smaller in the distance.
How many times have you debated it, Glober?
I think maybe that you're taking what they're saying wrong, because I don't think anyone would say that the fact that things get smaller as they go further away is evidence that the Earth is a globe. What we say is that because they fall below a certain point that you should be able to see them at, then that's why it shows that it's a globe. So if we look at Miles Davis' observation at Terrapin Law towards Forth Road Bridge, all right, are you looking at that for me?
Who, me?
Yeah, could you just look at the VMix core sec?
What? Right, okay, one sec.
Right.
Oh, yeah, okay.
Yeah, right. Yeah. So we're not saying that the fact that those mountains in the distance are smaller is that it's proof of Earth curve. What we're saying is the fact that they have fallen below the tangent of the eye line of 210 meters is what shows that the Earth is a globe. If it was just that they get smaller in distance, they would sink into that red line, not go below it. That's the claim. I mean, I'm not other globers, so I can't speak for them. I don't like to take what other people are saying in debates. You know, I'm not them. I refer to experts. But if I'm to look at this observation, we're not saying the mountains got smaller, therefore the Earth's a globe. We're saying that the predicted amount visible has fallen below the eye line, which is demonstration that it's a globe.
Well, as I showed you that image before with the wind turbines, it's clear to see that things can appear to drop beneath what you would consider the eye line. These things happen. It's just a function of.
Hey,
of
let
viewing.
me pull up my capture real quick because I have that. I'm sorry, we got away from that for me to go back and look at vMix. But if you'll just present my screen real quick, Fight.
Okay.
Okay, so with the limitations of the size of the picture and the limitations that I'm working with in Paint, of course it's just a step line, but it is a straight line in reality. Do you see how it's from one center of one wind turbine all the way to the center of this wind turbine right here?
No.
Do you see the top of the turbines go above the line?
Yeah. On
wait,
vMix?
yes.
Oh, no, you're not showing that again, are you?
Oh. Wait, hold on. I'm sorry. I thought I was sharing my desktop. Let me get to it. Yep. Oh, I am. In the wrong window. I gotta get my vMix set back up, guys. Okay, do you see it now?
Yes.
In that picture, I drew a straight line from this turbine right here, the center, and I tried to get as close as I could to this turbine. Again, like I had to, if I zoom out, the line looks a lot straighter. Let me get to zoom out a little bit so you can, oh, wrong way. So this was the original picture that you sent me right here in its original size. So I just zoomed in to make sure I drew a line between the furthest that I could tell, you know, because I didn't want to assume anything. So I just drew a line basically to the center point of the furthest wind turbine that I could actually physically see that wasn't obstructed, right? Now, why do the top of the wind turbines, why do they go above and then circle down to the point, the far one? Why is it not a straight line, all turbines all the way down from one point to the next, that they fall off linearly?
Okay, so you've drawn it to one that we can't see. How about you draw it to the ones that we can see? So there's definitely a turbine there that we can actually see the center of that hub. There we go.
This one?
Yep.
You want to talk?
So if you want to draw that,
right here, draw a line to that one. Okay. Yeah.
Yep,
give me 1 second to get that. Try to get this as perfectly center as possible. Is that center enough for you? Which one do you want me to
see.
It's kind of jumping between 2 pixels.
Yeah, he should be sharing it.
Yeah.
I should
Yeah, I
be
mean,
sharing it. So, okay.
Yeah,
so look, this was the bottom. Let me take it to the top
right
pixel
one.
because
I can't see the right one.
Fight, do you have me
You're
zoomed
too
in
close.
too much?
Yeah, you're too zoomed.
I think you've zoomed in
No,
too much.
I'm sorry.
That's
no,
better.
Look, here's the original image that was sent right there. Now, I'm trying to draw it from the center point to the center point. So you want me to go from here to here? I can
Yes.
Do that. Okay.
Okay.
All right. Is that good enough for you?
Yeah.
I tried to get it as close as possible. I can redraw it if you need me to, but I'm trying to do it as good as possible with the other thing. Now let me move it to the center so that way you can see.
Yep.
Again, even at that point, they still rise up above the line.
But what's your point here? Can you prove to me they're in a straight line, because they look to be curving back on themselves on the other one? And can you also tell me the distance between each one? Are they the same distance between each one?
It's your observation. It's your observation.
It's not my observation. It's an image I picked off the internet.
Well, I mean, it's your evidence that you presented, not that you took the observation, that you presented it.
Yeah, I didn't present it
the
for
way you
a line through the curve. I presented it to show that things get smaller with distance, and that you can demonstrate that very ably in this. And the way you would assume that you would be putting the center of your camera in, that last turbine would be beneath that. That last turbine would be beneath the center of where you would expect the camera to be. bit like Miles Davis's image that you just put up before.
Yeah, well, yeah. We're making the assumption that the camera is perfectly level. We're also making the assumption that there's no significant refraction that's being there. I mean, there's a lot of assumptions that we're making without having the supporting evidence to make those assumptions. So all we can say about this is that it's an observation.
Okay, yeah.
That's it.
And yeah,
it's not supporting data either way. To me, I would say that if you saw these things fall, if it was just a matter of refraction, since we don't have, there's no in the equation that Fight the Flat Earth said there was no exponential variables, right? There was nothing squared, cubed, or anything like that. So anything that we see, we should see as a fall off at a linear rate. Okay, so we shouldn't see the ones in the foreground falling off slower than the ones in the background, for instance. Here we see that it's not linear, that it actually does get smaller. I'll agree with you, they get smaller with distance. But it appears to me as though they rise up in elevation a little bit and then come back down.
But why would there just be a curve there?
Or Soundly's, I'm sorry?
Yeah, but why would there just be a curve
because
there?
The Earth curves up when you have it. Well, when you have an observer
Right,
height,
okay,
which
so
everybody pretty much has an observer height, you're going to have the Earth is going to curve up to the horizon and then curve away from you relative to
Do you know how big those turbines are? Do you know those center hubs? Those center hubs that you're looking at? They're about 4 meters. Those circle things that you're actually trying to view into, they're about 4 meters. They're between 3 and 4 meters depending on the size of the hub. The blades on them can be anywhere from 35 meters long to 60 meters long. Right? Yeah. So what you're showing here...
I know they're big.
So between these turbines, let's say they're half a mile apart, you're looking at a 3-mile stretch. What would be the Earth curve over 3 miles? 6 feet? So essentially what you're showing here is greater than curve, because the size of those hubs, the amount of distance to that center hub that you're showing this arc of is too much. God's sake.
I guess I don't follow what you're saying there. I'm just showing that they don't fall off linearly like you would, like the equation would predict.
Sorry, I dropped then for a second or two, so I just missed what you just said then. But yeah, my point was just that there's greater than arc there than what you would expect over that shorter distance. So it has to be something else. It's probably
again. We're on that. Assumption.
There's a lot of things we don't know about this picture. You're going to have to take into account compressed perspective based on the angle that we're viewing it and everything. Arguing about this picture is pointless because we don't have details about this picture. All right, but Miles Davis's observation is there's many reasons why I like this one, because you are away from the surface of the water. Right, at 210 meters, the lapse rate that you're going to be getting when you're looking straight out is going to be minimal compared to when you're at the water. So the refractive conditions of you looking at the mountains in the distance that are actually in elevation twice the height of the red line, that there's no explanation for why they would fall below it. Certainly not things getting smaller, because we all know things appear smaller in the distance. But that would just make the mountains shrink into that red line, not actually go below it like that. And again, the refractive conditions here are going to be practically zero because you're 210 meters above sea level.
I don't think that makes any difference. I think you've still got a gradient.
It does make a difference because you do have
the distance to those. Hang on, wait a minute. The distance to those mountains are about 100 miles away. Anywhere from 90 to 100. Some of them are 120 miles away, right? Yeah. Now, you're going to be looking through 120 miles of atmosphere that has a gradient to it.
Yeah, but not as much as if you're closer to the water. There's going to be a gradient, but it's going to be minimal. The lapse rate over that distance is going to be a lot less than if you were at the water.
No, because you've got a warmer atmosphere at the bottom, and you've got a colder air at the top. The light naturally migrates downwards through the gradients to the warmer atmosphere. So it's essentially, it's showing this sinking over 120 miles, bearing in mind, 120 miles, that's a long, long way for a photon, if you believe in photons, to travel. But ultimately, you know, we've got this sinking effect, as I said, modeled out by the globe earthers, you know, that have shown this effect to actually happen. So I look at this and I just think, you can't scale it on a very short. It'd be very difficult to try and scale this on a 100-meter track. I wouldn't be able to do it. I don't think you'd be able to do it over a couple of miles. Who knows? Over these sort of distances, it's very, very difficult to try and pin. But we do know that the sinking. You know, in your model, you have sinking. You have this effect of sinking.
Yeah, I mean, but that's the thing. That there is no form of refraction that would make everything fall down like that in the conditions that you would have between your eyes and the mountain there. You would have to have some extreme temperature inversion, which doesn't happen when you are that far away from the surface of water. That's the thing. That's why I keep saying we know the effects of refraction. They already have been quantified. That in that page that I sent you, the MC24/R, there's another link there that talks about the history of how they quantified refraction. You know, these are known values. So,
what do you think happens to the bottom then with heat? You know, do you think we can get things lost?
It depends on the temperature profile. It just depends on the temperature profile in all conditions. You can show me observations till the cows come home, but none of the observations you've shown me are impossible on a globe. I'm not saying that they're impossible on a flat Earth, but all the things you've shown me, based on our knowledge of refraction and our model, are perfectly explainable.
But what I'm doing here is I'm taking your idea of refraction and applying it on a flat plane, and I've been able to demonstrate that the same effect would happen. Maybe not to the same extent, but who's to say that the extent and the gradients that you've quantified are accurate?
And who's to say that the experts that measured them?
Yeah, but what I'm saying is that we can model it out. We can model it out on a. No, you can wait a sec. We can model it out on a flat plane too, and we can still see those same effects. You know, we can still see those same things happening. I'm not taking away the idea that this thing that like I say, that you've got this refraction, these gradients going on. In fact, it's, you know, that was my point of setting up this show and getting the Globers to come in and make these presentations. They actually produced evidence that showed on a flat plane, across a plane, you'll get this effect of sinking. Things will disappear from the bottom up. So I don't know how it's not even crossing your guys' minds to believe this, when I've had 2, 3, 4 Globers come on, very well renowned Globers, that have all said it's a possibility.
So I'm not saying that sinking isn't possible, but when you're at the elevations that we're talking about, you're not going to get that kind of lapse rate that will cause that temperature inversion to make those mountains sink to twice below what they should be if there was no atmosphere. But I think Team had a question for you. So
yeah, sure.
Yeah. So ranty. That at that pull that back up, fight.
Oops, sorry.
I
need to go and take a Riley.
Why? Why is the mountain 220 meters up or 210 meters up? Why is the 210 meters up onto that mountain or hill or whatever it is behind it? Why is that not eye level? Why is that not at the same level as the 210 meter pole that's in front of the camera?
Well, firstly, you've only got one point of view, so you've only got one post that you're looking at. You're not looking at two, which would level it for you. And secondly, like I've just explained for the past 15 minutes, that through a gradient, you know, you will get this sinking effect as the light naturally travels from the colder air to the warmer air.
Earth, there is no gradient. But in flat Earth, there is no gradient. You'd be looking in a straight line. You'd be looking in a straight line.
No, you'd be looking in a straight line, and you would see short to short. Hold on.
Pull up that, Ranty, Pull up
Hold on, you'd be
pull up the
looking.
picture that
You'd
had
be
the
looking.
yellow bands in it with the tower and the person. Real quick, I'm sorry. I don't mean to interrupt you, but you know, I want you to see where I'm
Well, you
coming
asked
from
me a
because I don't
question,
think you
and I'm
understand what I'm
waiting
saying.
to explain it to you, which is that we
But
already
your
went through this
explanation is
before.
contradicting what you just said earlier. What
We
your
already went through
explanation
this
contradicts
before.
what you said earlier. So
We already went through this before.
okay,
That
I'll
on
have to
a
wait for a fight to
plane,
get.
on a
Yeah, I
plane,
know, and
on a
you're
plane,
contradicting yourself.
when,
So.
for God's sake, do you constantly talk over
There's a
your guests
delay,
every time?
Ranty. Listen, Ranty. There's a delay between me and you. Don't worry about it.
Right,
Okay,
I'm
it's
back.
not me trying to talk over you. That's why I stop when you fight. Tell Ranty about our delay problem so that he doesn't think I'm
Right.
just trying to be a fucking dickhead.
He for some reason, right, Ranty, only between me and Team, between no one else, just between me and Team, there's like a 3-second delay. So Team's coming in through me to you, so you're getting the 3-second delay that I'm also hearing. I don't know why it happens. It's only
For
with
everybody in the chat. Yeah, for everybody in the chat, let's just do the ding test so everybody
Alright.
hears how bad it is, okay? Go ahead. I'm going to say ding, and he's going to say ding when he hears me say it, okay? You do
Okay.
the same, Ranty, so you know he's not bullshitting, all right? Ding.
Ding.
You see how long that was? It's not me trying to talk over you or trying to be rude. It's just it's an inconvenience of the way we communicate with each other.
Yeah.
So, please pull up that picture that you had up before so we can talk about why what you just said contradicts what you said earlier.
Well, I don't know. Firstly, I don't know which image you're talking about, and secondly, I haven't been able to
one with the
explain
tower and the
because you
person.
haven't let me finish a single sentence in the past 10 minutes.
All right. Apologies if we've been over talking you. I'm honestly not intending to do that, Ranty. What image are you referring to, Team?
The one with the tower and the person that has the bands in different colors.
Right. You right, get that
Okay,
back up,
let me
Ranty.
go
I'll get that back on the
We're going to
stream.
explain the Miles Davis observation using his image, and he's going to need to explain where his gradient pressure change or temperature pressure change that causes the mountain only to magically drop. He's going to have to explain that, and I want him to use that using this picture right here that he's already presented. So please pull it up, Fight.
All right. There we go. Just putting that up now.
Okay. Let me get you on full screen so I can see it. Perfect. All right. So if you draw a straight line from the eyeball of the observer on the right to the tower on the left, it will not pass through different bands. On a flat Earth, it will not pass through different bands of pressure, temperature, atmospheric gradient. Okay? It's not going to pass through that. It will be one straight thing. Everything from that point to the observer will not be bent up or bent down. It will just pass straight through. So that point should look in line with the 210 meter pole and the 210 meter camera. If it doesn't, you need to explain that.
Okay, so 120 miles, and you're going to assume that the temperature gradient is the same across the whole way, that there's no mixture going on, there's no difference in these gradients between them. They're all going to be perfectly
At
the same the whole way.
At 210 meters above sea level, you're going to get a much more stable line than you would at 6 feet above sea level. There is going to be at 210 meters. There is going to be much less of a change in temperature profile than you get when you're closer to the water.
We're talking about distances of 120 miles here, guys. We're not talking about a small distance.
But we're still saying that over that 210, over that 100 miles, sorry, the change in temperature, the actual lapse rate over that point, if the Earth is flat, will be minimal, bar some wind and stuff.
Can you? Yeah, exactly. Can you prove this? Can you?
No, because we don't have a flat Earth to prove that on.
No, but it's words like you're just saying that it can't happen.
No, I'm not saying it can't happen. I'm saying that the refractive effects would be minimal compared to being closer to the ground.
Have you got the refraction gradients from if you was at 210 meters in elevation?
Well,
across your globe.
Across the globe.
Across your globe. Yeah. Not at sea level. I'm talking about 200. If you're at 210 elevation,
right? Again, it's the difference in temperature that's the important thing, right? So what we're saying is that over that 100 miles between your eye line and the mountain, if the Earth is flat, that particular band that you're looking at shouldn't have that much of a change of temperature. Certainly not as much. I'm not saying there won't be any, because there's going to be some wind and stuff, but there's going to be a lot less of a change in temperature than if you were at a lower elevation.
Okay, so I just want to confirm this, because people like the Rumpus, and he's put himself on a pedestal here and says that he's the globe's lead expert on this type of thing. He's explained that even 1/50th of a temperature degree in change is going to affect the trajectory of the light.
Yeah, I'm not saying there won't be any.
So if we're looking across 120 miles here, we only need the minimalist of temperature change across that entire 120-mile stretch, the minimalist, 1/50th of a degree, to actually get a change in direction.
Yeah, but because of the fact that you're 210 meters above sea level, that change isn't going to be very much. I'm not saying that you're not going to get any refractive effects, Ranty. You always get refractive effects if you're looking at the atmosphere. But the higher elevations you go, the less refractive effects you get, because the change in temperature over a certain distance is less. If you are...
It doesn't need a lot.
No, it might not need a lot. It might not need a lot, but it's less. It's a lot less than if you are at the ground. But by saying you might not need a knot, is still not saying that it's going to make it shrink below the eye line. And for that to happen, you need a massive temperature inversion to actually cause that kind of. You do.
No, it'd just be a couple of changes. That's it. It doesn't take a lot
to make that kind of difference. It absolutely does.
No.
I mean, you can keep saying no, not really, but it's the physics of how refraction works, Ranty. You need to the important things that you need to take into account when you're talking about refraction is the change in temperature over a distance. It's called the lapse rate. So if you are close to the surface of the water, up to about 6 feet, you're going to have a much larger lapse rate than between 100 and 200 meters above sea level. That 6 foot will have a larger lapse rate than that 100 meters.
Yeah. So this is just 100 meters from just probably a couple of inches off the ground, just at 100 meters, and we're already seeing the effects, the downward trajectory of the light from these two objects. This is just over 100 meters. We're not talking 120 miles here, and we could already see.
That's on a racetrack that gets hot. It's not. It's not over water, and no one's denying that you can get these kind of refractive effects. But again,
that's why we're seeing.
But again, at that point, because the distance doesn't matter that you're seeing it, it's the lapse rate that is important, and the difference in temperature between the track and the top of the egg there will be quite great because of the fact that the track will be radiating a lot of heat. So you're going to get quite a large lapse rate there that is going to cause more refractive effects than if you are at 210 meters. No one's denying that you get the effects that you're talking about, Ranty. I agree that refraction is a thing that you see stretching and stuff. But it's
you're trying to put it in a box and say that there's no way that you can get that mountain to appear lower than the 210. Now that's just an assumption.
No, it's not an assumption. It's based on the knowledge of refraction. You aren't going to have a large enough lapse rate for that to happen.
No, it's not.
No, it absolutely is. Again, I'm not going on assumptions, Ranty. I'm going on known quantifications.
Oh, well, here's one for you then. So if we're looking at a building in the distance and we're seeing 100 feet more of it than we should over a distance of, say, 20 miles or something like that, it will be claimed that it's looming up. So that's the light raising up over that distance, right? So
it's not the light raising up. It's that the light has bent over the curve, allowing you to see what is further. So the light's bent down, bringing the image up.
Yeah, downward refraction giving you this effect, yes. But still, we're seeing 100 feet more, right? Just over a 20 mile. So you've literally claimed 100 feet there, right? And you've moved that from point A, lifted it up beyond Earth curve for you to see it. 100 feet, 200 feet, doesn't really matter. It doesn't matter. You've got infinite over 6R in your model. You know, literally infinite over 6R. And if you've got infinite over 6R, right, so you can see perfectly flat, right? And you've got these observations where you see perfectly flat from shore to shore, right? Now that's in your model is infinite over 6R. So that's with refraction, that's with looming, right? But you've also got sinking. You've got that same effect, sinking. And there's more for sinking than there is for looming on a flat plane. You can model it. You would have more sinking than looming.
Based on what mechanics?
On the trajectory of the light through the gradients. Naturally traveling.
And again, your eyesight, you looking out at a straight line, what you're looking at on a flat plane, there's going to be minimal refraction. If you're looking up or down, there's going to be refractive effects, but you won't be looking for a gradient if you're looking straight along on a flat Earth.
You won't be looking for a gradient. The light will have to travel through the gradients to get to you.
Not if only for things above or below you. If your eye line, your eyesight, a straight line in front of you, you're not going to be looking through a gradient.
Yeah, that's my point. Because whenever we get these observation days, when we get these days where there's no atmospheric turmoil, there's no turmoil over the water, there's no wind, there's nothing like that, we see from shore to shore, and you guys claim that's refraction. When literally what you've just said is how we could apply it to ourselves, which is, when we've got this equilibrium where everything is just still and we can see from shore to shore, that is what you'd expect to see. You would just get a direct line of sight. But we never see that because it's very rare that you get those days, which is why you can go out and you can film all year long and you might only get 2 or 3 observations where you see from shore to shore. The rest of them, they're all screwed up, messed up, inferior mirages, all this kind of stuff going on, weird effects going on, right? And that's because the air is dynamic. It is moving. You don't get these steady, stationary levels.
It's dynamic, but it's not mixed up like it's in a blender. There's still an average that is easy to get. There's still an average pressure gradient from 14.7 psi going up. And it's the same with temperatures. You can still get an average of the temperatures. It's not like it's all being mixed up in a blender. And the fact that you don't see those things most of the time, you only see it on days when the refractive conditions are just so, it kind of indicates the opposite of what you're saying. But the main point is, nothing that you have shown, or none of the observations that you've done, are impossible on a globe. They all work with the knowledge and measurements that we have. And again, this isn't going on assumptions, because I don't have to presuppose a ball because I go on measurements, and I don't have to presuppose refractive conditions or effects because we have quantified the effects of refraction. The only one that has to work on assumption here, Antti, is you, when you have to assume that it is flat and this is how it works, when there's no measurements or anything to back up what you say.
Why would you say that I've just showed you an image before that's shore to shore with a truck on the foreground.
That's not a measurement. Do you have any?
You agreed that it was a nice image. You agreed it was a nice image. It just looked like a nice image. Yeah. The problem is, like I said, that is in your model loomed up because the distances involved would have created an Earth curve that should have blocked that truck. You shouldn't have been able to see it. Yeah. So that beautiful, nice image, that crisp image, when we had just a nice shore-to-shore observation, in your model was being loomed up. It was all some kind of mirage. It was some kind of hologram. For us, we just see it. We just see it. We don't need it. We don't need it to be loomed up.
Go on, team.
Okay. So what I was gonna say there was, there's something along the lines of, okay. So when you're taking an observation, and it's just a simple observation, and you've made a point here that the reason I want to address is that you said these clear observations, right? Why is it when the days are clear, when we're looking over, on cold days, when there's no moisture in the air, it's perfectly crisp and clear, we can see great distances, right? Well, part of that reason is because when air cools, it condenses. When air condenses, it then increases its refractive index. So by increasing the density of the air and at the same time removing the moisture from the air, you're going to increase the amount of distance that you can see exponentially, because not only are you decreasing the amount of moisture in the air, which then also condenses the air, but you're also reducing the temperature of the air, which condenses the air. This is why these observations are always done over water and are best when it's absolutely fucking cold with no moisture in the air. That's when you're going to see the furthest, because there's no obstructions in that band of air, as well as it's very conducive to refraction over distances.
So ultimately, you're saying that there is no way we can demonstrate using optics what the shape of the Earth is then?
No, because we've got an atmosphere.
Not necessarily.
Well, no, T.
No, well, hold on,
Fight.
Okay, go ahead.
The problem is that we have an atmosphere, which means
Yes,
that everything we see is distorted. So we need to rely on physical measurements.
The first glober that I heard say that, because every other glober that we come across, they put us in a side-on view with no atmosphere and just a clear line of sight to it. So if you're looking at a truck that's 10 feet tall, it will still be 10 feet tall if you put it 100 miles away, right? Doesn't matter that you're reducing it in its angular size, but also
the actual size doesn't change, obviously.
Yeah, but you've got no atmosphere in the way. There's no blockage. There's no physical blockage. You're not seeing through the atmosphere. This has been our argument for the longest time.
I don't understand. I mean, we've always got an atmosphere.
Yeah, but when Globers come on to the shows like Nathan Oakley's, or they've come on to mine, or they go on to other people's, Arwen's, or whoever's, right, and they come on to debate, they come in and they act like they're stupid, right? And they literally, I'm hearing from you some clear thoughts, it's refreshing to actually come in and hear a Glober talk normally, like you would expect. Yes, we have atmosphere. Globers, for the most part, don't do that.
Right. I think the issue is that a lot of Globers are afraid of you guys with your gotchas. So they try to avoid, a lot of the arguments that you have are definitions of our model, which isn't what we say. And then you try to get in people in a gotcha by agreeing with a certain assumption that you make. Whereas I don't care about that. I don't care about being in a gotcha. I'm not going to deny that we have an atmosphere, which means that everything is distorted. I'm not going to deny that there is a container keeping the atmosphere. That container is gravity and the energy needed to escape it. But I'm not going to avoid using the word container because Stephen Warrior thinks that it's some kind of gotcha. It's not. Of course there's a container, but the container for the atmosphere is literally the energy required to escape the downward force caused by gravity. So I think a lot of it comes from them not wanting to be caught in these gotchas, and the moments then where Nathan Oakley will start screaming that he's raping you with your R and stuff. They don't want to get caught in those moments. But I'm not afraid of using words that are right. So maybe that's why you're getting that from me. Because yes, we have an atmosphere, which means everything we see is distorted. There is no way to see the geometric horizon because there's an atmosphere in front of you. The only way to see the geometric horizon would be to take away the atmosphere, and we can't do that. Which is why we have to rely on physical measurements instead.
Can you pop this image on the screen for me?
Yeah, one sec.
This is just following up from what Team Skeptic was saying. Essentially, obviously, when you've got clearer days, less water in the air, you can see much further. Well, here's a perfect demonstration of that. So this is your average day. This has been my average day for the past year, I would say, down at the bottom image, where you've got this massive inferior mirage running through. You don't see this sand dune that's up there. You don't see, that's the inlet. You've got a little sliver of blue there that's the inlet, and then you've got the the houses that are on the seafront, basically down here, going all the way through. So 18 miles away, I think it is, 18.3 miles away to those buildings over there, right? But mostly you get an inferior mirage that just blocks off everything. You don't see the sand dune, you don't see the inlet, you don't see the houses.
Okay.
Right? Now, in the globe mathematics, funnily enough, globe mathematics say that the bottom image is what you should expect to see on a globe. All this blockage is what should be there on a globe. But yet, the top image, the clear image, the image where we're seeing from shore to shore, we're seeing right down into the inlet, right down to this shore, to these houses here, right? We're seeing these, we're definitely seeing them, but that is all contrary to what there should be on a globe. You shouldn't see that. But this is normal. This would be perfectly fine on a globe. All this this mush down here. I mean, all this refraction going on that's messing everything up, right? That's perfect for a globe. But the clear days, when you see shore to shore, when there's none of these particulates in the air, there's none of these exaggerated refraction things going on. So you just see, you're avoiding those refraction things.
Okay.
You're just seeing shore to shore.
Now,
right.
This is our point.
What would you see there? Right, now, make the assumption here that the Earth's a globe, and there's no atmosphere. What would you expect to see there?
I would expect, if there was no atmosphere, pretty much the same as this, but I would see that this sand dune wouldn't be in the foreground. This water would be higher up. You'd have this water that would just envelop the sand dune.
So you'd have much more of a physical line that would show you.
You'd have a hump, yeah. Yeah, you would have a hump, a physical line.
Right. Now, but we don't see that. Because there is an atmosphere. No one's... well, I'm starting to wonder about like what some other people say, but no one...
No, but like Team Skeptic has just said... Team Skeptic has just said it, literally just said it for us, which is that when you don't have these refractive issues going on with these distortions and these wavy things going on, you actually just see a long way, and that's perfectly fine. Because we agree with that, because it negates the atmosphere. Because the atmosphere is the issue. The atmosphere causes the blockage. Flat Earthers' main problem with these observations is the conditions on the day. It is the refractive problems, the issues that you're getting with these smudges, inferior mirages. But we just see nice shore to shore.
The picture above, the picture on the top is the one that's more heavily refracted. The picture on the bottom shows more distortion. The picture on top has more refraction. That's why we can see further.
Well, I mean, distortion is...
You're taking a ball and you're rolling it...
Yeah.
Well, yeah. It's. I'm saying, like, what you're doing is you are increasing the refraction by decreasing the amount of water vapor in the air. Also, okay, we'll wait for him to come back.
Oh, you're back. Okay, sorry.
Okay, he's back. Okay, great. Pull that picture back up, Fight, please. That Renty had up. Okay, so what I'm saying is that due to the lack of water vapor in the air, you're going to decrease the distortion. So now you don't have to have the light traveling through the water vapor in the air, being distorted and whatnot. But also by doing that, you're increasing the density of the air in that same observation, right? So when you increase the density of the air, you increase the refraction. That is, when you're working with two gases or the atmosphere, which is very similar to one another, simply increasing the density does increase the refractive index. So you're seeing more refraction on top, but less distortion.
Right. So, but the problem is that the density part of, or the density pressure part of the equation is minimal in comparison to the temperature. Minimal. So you wouldn't expect to see an awful lot of difference.
Well, okay, so when we remove the water vapor from the air, obviously we make it more clear, less distorted. You would agree, right? I mean, if we're not looking through all that water vapor in the air, you can see the buildings more clearly, correct?
Well, yeah, you see shore to shore. This is impossible on the globe, and all we're saying is that.
Yeah, well, I'm saying
the
any
atmosphere
observation.
Itself,
I'm saying any
the
observation.
The atmosphere itself is giving you the effect of this curvature. This is what it is. This is what it does. It's assimilating this idea that you can have this curve. When you remove the atmosphere, essentially, like what we're saying here, we're not removing the atmosphere, but we're taking away the blockages. We're taking away those issues that are causing us not to see very far. We just see shore to shore. right? We're looking for
Right,
demonstrations of looming here that proves your argument. There is no demonstrations of looming. We can say that there's definitely blockage. There's blockage on this bottom image, which is the norm. You get this inferior mirage. This is pretty much the norm for me, at least, anyway. Very rare you see these beautiful images at the top, but you do see them. The problem is that this isn't looming up. This isn't being loomed up. There isn't a physical. This isn't being loomed up. The post in the foreground.
You're making a claim there that is contrary to the quantification and known effects of refraction. You're saying it can't be loomed up,
my
but
question to you,
it absolutely can be, and it isn't an issue on our model, which is my main problem with all these observations, right? No matter what you can see, none of them are impossible on the globe with the known effects of refraction. What I would love to see is something that is impossible on the globe.
Okay, so if this is being loomed up, right? Now this post is only 4 miles away, and the buildings behind are 18 miles away. You would expect to see a relative change in their distances. If this is being loomed up in the background, right, and this post is only 4 miles away, that's 18 miles away, you'd expect to see a difference between where this post is in relation to this building behind it, and we don't see that. We do not see that.
I would argue that, because Ranty, can I point something out here real quick? Ranty, on the bottom image, can you put your mouse cursor on the right side of the pole where the yellow and the dark side meet on the bottom image? Right there, exactly. Now, if you were to take that cursor and go directly left and try to keep it as short or as straight as possible and go just to where that white garage door meets the dark area. Perfect. That's exactly where I'm saying. Do you see where that's at in relation to the door? Now go to the top image and do the same thing. Look how short you have to move it left to right, number one. And number two, look how much further it is from the bottom of the garage to the top of that where you have the cursor at. I mean, the refraction in this image causes many different things to happen, and there's no, unless you have quantified it, you don't really, it's just an observation. It's not really evidence to contradict the globe.
Yeah, so what you've done here is you've dragged everything down to the mush. You've dragged everything down to the mush. I'm looking at the top of the post, the top of the building that's out of that mushy air, to the top of the star here that's also out of the mushy air. Same here, that's higher. The top of the star is avoiding all this mushy air down here and up here. And you can measure that, and it's the same distance apart. There's no difference. You've got all this distortion going on. I'll give you that down here, because this is what happens with the inferior mirage. It messes everything up. But when this post is out of that, the top of that post is out of that. It's avoided it. Same as the building in the background. The tops and the tops, in relation to each other, there is no difference between the two. Now, if this is being loomed up in the background, right, rather than just an optical blockage, if this is being loomed, right, then that should be higher up in relation to this post, and it never is. In fact, I've taken so many observations from this spot and never seen any difference between the top of this post and the top of that.
Why should it be? I mean, to make that claim, you have to know the exact temperatures and stuff of what's going on there. To say that we should have to see that, it doesn't make sense, because what we're seeing is because of refraction.
But this was my whole point in trying to find refraction. When I said I was going to go and spend a year trying to find refraction, this is what I did. I went and I tried to film this post and this building every single day. And I built up such a catalogue. There was never any difference between the two. This building never changed its relative position to the top of this post. And when I said I went to go and try and find refraction, looming, I literally tried. Couldn't find it. And it was something that I actually put out on my shows, put it out on Nathan Oakley's at the time, because I was doing it, and I was showing this daily, showing that there was no change in the relative positions of either of these, which was demonstrating that there was no looming going on for this building behind.
I mean,
some days we'd see short.
It doesn't demonstrate there's no looming. It just demonstrates that the refractive index gives you that apparent perspective of what you're seeing. To make the claim that it's something that you shouldn't see, or you should have to see this, you would need to supply data like the temperature gradient that there should be. None of what you've shown is impossible on a globe. I'm not saying it's not something that is possible on a flat Earth, but I'm saying that it's something that is possible on a globe, which means it doesn't disprove that there's a globe. And
Okay.
that's why my question always goes back to: is there any measurements that any of you guys have taken of the Earth being flat?
Yeah, Ranty, can I ask you a question? So the yellow pole out there, how tall is that yellow pole, would you say?
Well, it's 4 miles away and it's out in the ocean, so it's hard to tell. But I would say somewhere between 20 and 30 feet in height would be my guess.
Oh,
Probably closer
okay,
to
so
20.
it does have some significant height. Okay, so it's not just like a
Yeah.
little piece of concrete coming
Oh
out of the
no,
water.
no,
Because
no.
I was going to suggest the same thing that Fight was just alluding to here, because you said that you have a catalog of this observation. I would recommend, and I would really be looking forward to seeing you try to do this, but try to take some GPS measurements. Go out to the pole. I don't know how much access you would have to that thing, or make a mark on it, or put something that was visible up there and mark it with a GPS marker so you can get a latitude, longitude, and elevation on it. And then go do the same thing with the buildings in the back and kind of build yourself a way of
Well, I know where it is.
modeling this
I know.
out so you can.
Yeah, it's called the star pole.
Okay.
It's a marker. It's a marker. You can find it. I've got the data on my Google Earth, so I've actually positioned it on my Google Earth, so I know exactly where it is. The only thing I don't know about it is its height. Now, obviously, where I live, we've got 9 meter tides, so the tide goes in, the tide goes out, and
Oh shit.
obviously it doesn't go out the whole way to this, but it certainly affects it. The tide goes up and it goes down it by probably a couple of meters at least. So it's never going to be the
Are
exact
these
same
both
height above
taken at
sea
the
level.
exact same time? Are these taken at the exact
No,
same
different
time?
days. But there's around about there's two different steps that I go to. This just happened to be something that I threw together recently today, actually, just to show you this. But this post here, sorry, my observation from this one here is about 50 foot. It will be 50 foot further away than this one. This one was 50 foot nearer. There's just two sets of
That shouldn't
steps,
make
two
that
sets
that
of
shouldn't make
railings.
that much. That should.
Yeah,
I
that's
don't think
what
that should
just
make
a
that much of a
very
difference
slight.
unless you were
Yeah,
dropping in
that's
elevation and getting closer to the water. That'd
no,
be the
no,
only time
no,
it would start really
but that's
making
just why there's a
making
slight
a difference.
parallax on this. But no, I've got hundreds of these
Yeah.
images in this spot here. But this was just a nice image that I picked up for the Inferior Mirage. Um,
Okay.
I've got
Yeah. I
so
mean,
many,
like I said,
so much stuff I could
with
talk
the
about.
I can just tell it's just the bottom picture just has a lot of refractive effects going on. While I say there's more refraction in the top, I mean more of the generalized refraction where the bending of light where you can see a further distance. But at the same time, like Fight was saying, even distortions are really still forms of refraction as the light passes through. Let's say you're heating up the air, and you would notice that the same way everybody does when they go out on a hot day and they look at the concrete and they see the wavy lines going up. That's just the heat, the light being refracted through a different medium, through a different temperature of medium. So obviously we could see that on the bottom picture. We don't see that on the top picture. It really does match what I'm saying. This is a prediction. This would be a predictive, something I would predict before you ever even showed the pictures. If you said, hey, I have one picture that's taken on a day with no distortions in the air, looks as it appears as to be a low humidity day where there's not a lot of water vapor in the air, I would say, well, your image is going to be clear, and that's going to be the image that you would be able to see furthest away with. Not simply because it's clear, but because it's also because the clearness means the removal of the water vapor, and then the removal of the water vapor, the second part of that is it increases the density of the air around it, it increases the density by removing the water vapor of that patch of air, increasing the refractive index. And the way to do that is to cool that area down, and temperature, like you said, also has an adverse or significant effect on refraction. So we're really, in the top picture, you're really putting all the sight distance eggs in one basket, the conducive eggs in one basket. You're saying, look, in this picture, everything worked out to where I could see the furthest, and that's exactly what we would predict on the globe model.
Can I just share this last image with you guys, because I'll need to be getting away. But ultimately, I think, you know, there might be a kind of like a misrepresentation of what you think I am actually doing with my channel. I'm not trying to show shore-to-shore observations. That isn't my point. My point is to show that these blockages that we see from the bottom up are, you know, not proof of Earth curve. That's what my whole channel is about. It's not showing the shore-to-shore observations, although I do have them, you know, and it's great to show them. But it's more to show that these effects that you think you're seeing with Earth curve are not what you're actually seeing as Earth curve. Now, 2.5 years ago, like I say, this center line, this inferior mirage through these three images here, was your globe Earth edge. You know, it was the edge of your sphere. We had so many arguments with everybody over this for years, until I went on this massive mission to actually find out what was going on. Is the inferior mirage actually the edge of your sphere? And I was able to demonstrate that it isn't. Now, you can see on the boat, so this is the boat, the famous boat that you guys say goes over the edge of the curve. Well, you can see the inferior mirage running through the boat here, and it just gets worse and worse the further the boat goes away. The actual inferior mirage goes higher up the boat. The boat gets smaller with angular size, and it just disappears into nothing. It just completely disappears. Here's the other image that I showed you where they had the truck on the shoreline. Again, the inferior mirage running through here. And the last one, which is an interesting image, is there's a dog here. This is a dog. There's their owners. Now, this dog, it was only a mile away. How do I know it was a mile away? Because they had a ramp that they came down, and I knew where I was. They walked down the ramp. I was filming them. It was a mile away. My camera was set to 3 feet, and I was getting this this effect. In fact, this dog completely disappears in some of the frames. This was taken on a video. So here we have probably a 3 or 4 foot high dog bouncing in and out of the inferior mirage to the point where it just completely vanishes. You got the inferior mirage of the human's legs down here. Well, that's just blockage of the real legs. You know, that's just a mirror image of themselves. That's a mirror image of the sky and the dog. But his legs are missing, his body's missing. It's all hidden behind the inferior mirage. Now, that isn't Earth curve. I had direct line of sight to this dog. You know, it was only 1 mile away and the camera was set to 3 feet. But it was hidden behind an atmospheric blockage, the same as this and the same as the boat. You know, and that's what my channel is about. It's showing these different effects, understanding what's going on with what happens when we're looking through these things. And then on the days when you actually see really crisp, great images, I've seen a boat at nearly 20, I think it was, hang on, wait a minute, 27 miles away from an elevation of just 10 feet. I was able to track this boat 27 miles. You know, and so you do get the days when you can see really far. You know, it's like on this day you see very far, clear image.
Off into obscurity? But when
it
you were
just ended
that
up.
boat,
It was
did
so
disappear
slow.
into obscurity, or?
Yeah, it just
But you
disappeared
didn't pull
into
out
a dot.
a higher resolution. I mean, there's
I had
like.
a P900
Can I show a picture real quick?
time.
I'd like to. I'd like to explain this observation, and give me 1 second to get it up real quick.
That's what she said.
Nah.
Yeah, right. Okay, so I'm going to play this observation. No distortion, no anything, but the ship still appears. And I'm sure you're aware of this observation because it's Wolfie 6020. It's gone around.
Yeah.
It's gone around the internet and whatnot. So why does that ship appear to be beyond the horizon bottom first when we don't see any of the inferior miraging that needs to be going on for your explanation to be sufficient?
Yeah. Do you know how far away that boat was in the distance? Just out of curiosity.
Pretty sure he says in the description.
I don't particularly. I think it does say in the description. I'll pull up the description 1 second. Let me get that.
Yeah, that'd be great. So, but yeah, I've seen this observation.
It's about 26 kilometers away.
Okay. And what's the boat in the foreground? How far away is that? Do you know? And what's his observation there? Sorry, I'm just curious because it's been a while since I've looked at this.
Yeah, it doesn't say in Wolfie's description how far away the boat is. Let me go to the original poster and see if it says that. Let me see. Okay, so it does say in the description, you may not be able to read it, It says that it was more. It gives the longitude, latitude of where the ship was moored at. So it doesn't have a distance on here, but it has the longitude, latitude of the camera with the elevation, as well as the longitude, latitude of both ships. So it's I can do that, I guess, real quick. I can plug it into a distance calculator with longitude, latitude, if you'd like. But I would assume it's probably 3 to, if that's a 10 meter height, I think is what he said, that thing. Probably about maybe 5 to 10 kilometers out would be the front ship. And like I said, it says 26 kilometers in the back. I can do the calculations if you would like me to, but I'm assuming that that's about what it's going to be about right.
Yeah, and then
No, that's fine.
there's also this observation from Dazza the cameraman that shows the ship disappearing quite nicely without any kind of inferior miraging or.
Well, it is the Inferior mirage that's hiding that, actually. In fact, the original boat, there's a very similar. In fact, it probably is the same boat that's actually here. That I've filmed this in the UK and around Liverpool, and it's exactly the same. And when you actually superimpose the original image over the top of that, it matches up perfectly. You see in just short to short, it's just the Inferior mirage that's hiding that. Funnily enough, even though it doesn't look like
the Inferior mirage? Like we don't see
it's
any
just
kind of
like
distortion.
The Inferior mirage in that.
Yeah, you are seeing it. It's definitely there.
Well,
It is definitely
okay.
there.
In your picture of the dog, but an inferior mirage results in a reversal of the image. So because of the way it's bounced up or the way it's bent up, it has a reversal of the image. So we should see a reversal of the top of the ship towards the bottom of the ship. Same way that we saw the reversal of the top of the dog at the bottom of the dog.
Yeah, you do. You do in that image. I mean, if you want to bring it back up again, you can go through that. But you definitely see it, and you actually see the sky repeated down underneath it too.
You were saying about Red Pill Philosophy earlier. It's now been 162 days, 2 hours, 10 minutes, and 4 seconds since he refused to debate me, even on his channel. Just saying.
Hey, Fight, can you bring that picture up that we were just looking at?
Oh, my one.
The
Dazza the cameraman.
Yeah.
Where did it go?
Daz's.
Oh, bloody hell!
I don't see the sky loomed, or I don't see the sky as an inferior mirage in that picture.
Yeah, it absolutely, absolutely is. Right, let's zoom. Can you zoom in on that so I can see that and take a print screen? Yeah, you can see. You see on the right hand side. You go across to the right hand side. Can you see those lines that are going down, 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 and down?
Yeah.
Hold on, let me.
Yeah, that's the Inferior mirage, and you can actually see the sky underneath it. So absolutely Inferior mirage, and you can see it on the left hand side.
That's these bits at the top of the.
Go back. That I'm sorry, I just don't see that. I see what Fight's showing me here.
He's saying that the little lines are an inferior mirage, but that's just the top of the. Let me get it right. You can see I think it's cages or something they've got on there. I don't know, but it's just the top of the structure that you're seeing.
Well, no, it's just a very shallow deck.
The inferior mirage. Go ahead. I'm sorry.
Yeah, the boat has a very shallow deck. I've actually looked into this image. It's a shame I don't. It's a shame I don't actually have it to show you. But yeah, you might have to just take my word for it or not. It's up to you. But I have actually analysed this one, and it's perfectly.
So Ranty,
it's just hidden behind.
Okay, so basically, with the inferior mirage, as you showed with the dog, it wasn't an exact mirror of the dog. It was simply like maybe the top 2/3 of the dog flipped upside down and attached to the bottom of the dog. That's the way the inferior mirage hid the actual true bottom of the dog. Okay, so if those, are you saying that the inferior mirage is simply somewhere between the top of those little poles and the bottom of the little poles? That's where the horizon, the inferior mirage begins?
Let me share my screen. I'll show you where it is, exactly where it is. Where are we? Here we go. Share screens.
One second, let me get you back up.
Share screens, that one. Boom. There we go. Right, so let me know when you can see.
Yeah, we can see it.
So the inferior mirage on this is right there.
Yeah.
Well then, Okay, hold on. Can you flash the red? Can you remove the red line
So,
and without deleting it, so that you can remove it and bring it back, remove it and bring it back?
well, I won't be able to keep
Okay.
removing it and bringing it back on paint.
Perfect.
But,
No,
but that's where
I
it
mean,
is.
like not move it and bring back. I'm sorry. Take the red line away and then bring it back. You know what I'm saying? Not zoom in and out.
So
Because
undo
I
and then
want to point
redo.
something out over here. Okay. So if you look over to the right, we'll call them the H. Okay. There's two H's on there. The one on the left, one on the right. Below the one on the
H.
right, there's a dark box-looking thing. You see that? Like below the yeah, that right there exactly. Why is that? Why
Yeah.
are we able to see that when it should be the atmosphere above it that's being inferior miraged in front of it, the same way we're seeing an inferior mirage covering the bottom of the everything that was below the red line that you just put up there.
Yeah,
Put the red line up
that's
again,
pretty.
please.
Yeah, okay, that's pretty easy to explain. So obviously you got your inferior mirage here. That's the hull. That's part of the hull of the boat, and the hull is just like that height. That's all it is.
But it's not.
It is. It
That's
is.
not
I've
the
got the.
hull.
It is.
How?
It is. I've had the. It is. It's the boat. It's the design of the boat. You can, if you. I tell you what. I'll send you the image tomorrow if
That's
you
on the
like.
that's on the
But
deck
look,
though.
look,
That's on the deck. We
look,
see it right here. That's
Ranty.
on
Hang
the
on.
deck.
Hold on. Just let me finish. And this post, these cranes, I like these cranes on it. That's why you're seeing it go all the way down to the floor. But if you look on the right hand side here, you can actually see the sky underneath it. So you can see that the sky is underneath it. That's the hull of the boat here. That's the
But
hull of it.
all right, look back at VMix because I'm showing you the other ship that is identical to the one that's hidden, and
Phoenix, right? Yeah.
yeah, you can see that underneath the H, they've got these cage-like structures. That's what you're seeing.
What here? These
Yeah,
things.
that's on the deck of the ship. That's
Yeah.
not part of the hull.
Yeah, that's what you're
Yeah.
seeing in the other thing. You're not, that's
Everything
not the
underneath
hull.
that is covered by something. Everything underneath that is covered by something.
So you're not seeing the hull of the ship in the other thing. You're seeing the top of those cage-like structures, whatever they are.
No, it's just the angle. Don't
Yeah.
forget, this is nearer to you, and this is further away. You've got a parallax issue here with where you're actually seeing these structures in relation to this,
Yeah,
as
you can
opposed
see
to over
that.
here.
You can see that they're shifted to the right slightly, but it's still those structures that are there. It's not the hull of the
Do you know
ship you're seeing.
Do you know the distances between these two boats, just out of curiosity, and the observer height?
It does say it in the description. Let me get it up. Oh god, I can't even find the.
Sorry, Ranty, I was in the Navy, and that's not the whole of the ship.
I was in the Navy also. Oh,
You swam in the ocean. That's not being in the Navy.
All right, I'll send you the link to that so you can get the details of it yourself, Ranty. I can't make my computer do what I want to right now. But you did say that you need to get off soon, right? Oh, he's disconnected again.
Did we lose him again?
Yeah, I think so.
He'll be back. They all come back.
I thought he was being quiet. Oh, right, he's back in Hangouts. Just wait for him to reconnect to here. Must be having internet issues. When he comes back, I know he said that he's got to get off soon, so we'll go over super chats and Ranty can answer any questions that are in the chats towards him. So if you've got any questions that you want, guys, I'll try to cover as many as possible. Just waiting for him to come back. Oh yeah, I wanted to show him Tampa Bay as well. Is he coming back?
Have to bring him back on.
Yeah, I can see him in Hangouts, but he's not joining the VMix call. I'm pressing the wrong buttons all over the place here. All right, I'll start going through super chats while we're waiting for him to come back. John Rapp for $2 Australian. Everyone say hello to John Rapp in the appropriate way. Lurking while working, so get on your game, guys. I think we've done well. And John Rapp for another $2 Australian says, good day, Team FTFE. Hello. You there? Oh, I thought I heard him for a second there. I must be hearing things. Okay. Good day, Team FTFE, Ranty, Sean, and especially the chat.
Hello? I thought I heard it for a second.
Oh, what am I playing that for? I think that's coming from his thing. Weird.
Hearing things.
Oh, the joys.
Oh, there
of
we go.
streaming
You're
with
back.
Fight.
Right.
The wonders of
There
modern
we go.
technology. Right, I know you said that you needed to get off soon, so how about we go through super chats, and if there's any questions towards you, you could give an answer.
Yeah, sure. I can stay another 10 minutes, and then I'm.
Also,
I'm
I
gonna go to bed. I'm tired.
yeah, I know it's quite late for us here. I do appreciate you coming on and having a civil conversation. It's been much more fruitful than with the dumbass that is Sleeping Warrior. Right, so we've got another one for second best Bob for £5. FTFE and Ranty together at last. People think that we're in a relationship now, Ranty. And FE News for
Well,
two.
Ranty, you see, he rocks your haircut hard, bro. So he stole that from you. I have scientific evidence that Ranty had that first. So fight. That's you've been copying Ranty for a long time now.
Yeah. FE News for $2 says, for the record, Craig has a beautiful body. David Oliver for
Lies.
David Oliver for £5 says, Ranty, the black swan proves looming and refraction exists. Do you agree with that?
Sorry, say that again. Sorry, I was reading something then. Sorry.
David Oliver says that the black swan proves that looming and refraction exists.
I disagree. I do believe that there's, there's some distortion.
Yeah, I think they're talking about obviously the crane on the left.
Not again.
No, you're here. You haven't left. Hello? I can still see him in the call. Oh no, he's dropped out now. Oh my goodness, he's having major issues with his internet. We'll just keep going on. Sparky NJ for $5 says, FTFE, if you fly my wife and I over, I would install a backup generator for you. You do have to feed us and show us around too. Thank you very much. David Oliver for £5 says, show Ranty Mr. Sensible video about looming. Yes, I did. Oh, you're back, Ranty. Thank you. The wonders of modern technology, eh?
This damn internet.
I know. It's been bad for everyone at the moment, I think.
Is this why they're getting the 5G up? Is this why they're wanting to put the 5G up? Yeah.
Glass Monster for $2 says, now I have to throw away my Superman shirt. Rocking the Superman shirt there, Ranty.
I put the Superman shirt on because I noticed that you'd put it in your image of me.
Yeah.
So I thought, well, you know what?
Why not?
I don't
do
mind.
It. Appreciate you playing along. Mikey Riot for £5 says,
Yeah, I
Ranty.
appreciate that, man. Superman's awesome.
Yeah. Mikey Riot says, Ranty, you seem like a normal person. What the fuck happened to make you ignore evidence and science? Was there anything in particular that happened to change you to a flat earther?
Well, I was always into conspiracies, so I was following everything from basically 9/11 right up to chemtrails and such, and I ran out of things to watch, so I thought I'll look at the one thing that I've always just laughed at, which was the idea that the Earth was flat. I didn't want to look into it at all. It was like ridiculous in my opinion at that time, and I looked into it. I watched a few videos. I thought, you know what, I'll go and buy a P900 because I knew that I could see Barrow in Furnace. I just wanted to calculate it for myself to see whether or not it matched the globe mathematics, and I just wanted a new camera anyway. But I went down and I was surprised to actually see that I could see far further than I should do on a globe. So that set me off. And that's one thing we do have in common is that, often, you know, and you have to agree that we do see further than we should.
Yeah, I mean,
you
of
know,
course, refraction does make that happen. And, you know, I'm not going to, like a lot of other globers, I guess, do, avoid using certain words because it fits into the flat Earth narrative. Yes, we can see further than a geometric horizon would allow us to, but that's because there is an atmosphere. But anyway, welcome to the members. Glass Monster, you are a scrapper. Thank you for joining. You can now use the awesome emoji of Nathan Thompson in jail. Then we've got Glass Monster, who says he's going to get an FTFE shirt to replace his Superman one. Thank you. Better charge for $2 New Zealand dollars. Says team, she's still waiting on her sandwich. No, team? Guess he's gone.
I'm sorry, my mic was muted. Who's waiting on their sandwich?
Better charge.
He's getting a mayonnaise sandwich tonight on my gaming stream.
Harley Halicus for €2 says FTP. I sent you a PM in Discord. Take a look. I've got so many things in my Discord. I'm sorry. I'll have to take ages going through them. Flat Earth News for $5 says globies are all talk, no experimentation. I can explain that, so no science. Yeah, all the observations and everything have been done already. That's cool. FE News for $2 says globies draw cartoons and never give experiments, apart from all the stuff we do. 3-1 for $2 says my 9-year-old wouldn't need it this dumbed down. That's mean. James Richards says for $5 FTFE said flat earthers don't do observations while giving credit to Ranty for doing them. He later admits that he doesn't do the observations. Yeah, I quite clearly said that I appreciate the fact that people like Ranty actually want to go out and do the observations, and I'm not in a position to do them. But the majority of flat earthers just parrot what certain people say. So at least Ranty's doing the observations. Better charge for $5 New Zealand dollars says, damn team, colour inside the lines. I bet your colouring book looks like my 1-year-old's.
Ha! It probably does. I am the most non-artistic person in the world, so anytime, like, I can't even dream what a perfect circle looks like. So,
James Richard for $2 says, FTFE, why don't you shout out your super chats? I'm doing that right now. I think he's a flat earther. I'm not sure. Nerd Angle for $4.99 says, advance on NASA shill money. Thank you. Please, no more free lessons on refraction. These fools just need to go back to school post-grad classes, boys. The Plot Hole for $2 says, another flurf who doesn't see evidence. Shocking. David Oliver for £10 says, Ranty, the black swan image with those rigs in the water are smudged and distorted, yet you claim that as evidence, yet in other photos the horizon is lower. What do you think, Ranty?
There's been many observations of the black swan now. The guy's gone back multiple times and captured it on with better conditions without having those bendy cranes. So I think that's a null and void argument for now.
Okay, Nuga for $1.99, quoting Nathan Thompson, says, lights in the sky change colour sometimes. Yeah, Nathan Thompson's a fucking idiot. James Richard for $5 says, FTFE's, his experiment shows the curve of the ball. Tell him to zoom in until he can't see the curve, like reality, then do it. No, it doesn't show the curve of the ball. It shows the horizon and things coming up above the horizon. John Rapp for $5 Australian dollars says, 510,100,000 kilometers squared surface area of Earth. Why arguing about 80 kilometers squared? Where's the edge? Tens of billions of people and no one's found the edge of flat Earth yet. Ranty, why has no one found the edge of flat Earth?
Who says we have an edge? Who
Fair
says
enough.
we have an edge? You know, we don't know how far. I mean, Admiral Byrd found extra land.
No, he didn't.
Look into that.
I've actually been scripting a video about that. Aaron Armstrong for $5 says, keep being polite, guys. No need to call people names like Mario or Luigi. Well, it's fine with Red Pill Philosophy because he does have an absolutely fucking ridiculous moustache. Looks like Mario, and I reckon the only reason he hasn't debated me is because he's too busy saving the Mushroom Kingdom. C4 for $5 says, Ranty, you borrowed my shirt for long enough. I would like it back, please. Did you steal his Superman shirt, apparently?
I did. He wants it back, though. You can have it tomorrow.
JL Warren for $4.99 says, Ranty, can you debunk the globe with demonstrable evidence?
I think it's very difficult for even the globers to prove the globe using proper evidence. The scientific proof, you can't. I don't think there is a way of doing that either. So, catch 22. Unless we can go up high enough one day to actually look back. you know, maybe one day we'll get that. See the curve.
Christopher Hugan for $2 Australian says, every time you touch your P900, you prove the globe. Yeah, that's a good joke. Sleepy Dan for $2 says, why don't flat earthers take measurements? Oh. Do you think you might start with your observations, maybe trying to take a temperature profile?
Possibly. I mean, I've done all the measurements. You know, I've done all the measurements very consistently, so that I'm, you know, exactly know my observation height, etc., GPS locations. I mean, I could be a walking Doppler radar at some point, I'm sure, if I really wanted to, and have all the gizmos on me. But you know, there's only me,
Yeah.
and you know, there's a lot of things, especially where I live. You know, you've got the tide that comes in at probably a rate at times of probably around about 20 meters a minute. You know, and you're rushing away from that. You've got to hide from that thing running in. You know, so I've got to be mobile. So I've got a limit to how much I can carry.
Fair enough. Go on, Team, what are you going to say?
I was just going to say that I believe that you do enough work that you could take your observations a little bit further. You could actually, in my opinion, Ranty, you could go and take like 5 or 6 observations, use those as the control observations, and then pick a random spot and make a prediction based on your control observations and the shape of the Earth that you believe it to be, and test that prediction to see if it matches what you find it to be in reality. And I believe you understand what I'm saying here, correct? Like, I think you're in a position that other flat earthers are not in to be able to make that happen. And me personally, that's one of the reasons why I don't even bother addressing any of your videos. It's not that I believe that you're right. It's just I believe it's insufficient amount of evidence. It's the same as just some person randomly saying the Earth is flat because he uses his eyeballs to see that it's flat. I think you're in a different position than that person to be able to make measurements and provide data with your measurements that help other people to make predictions based on your data.
I've how many? Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. So I put together today. I put together 9 folders inside this FTFE debate. We've only talked about 2, I think.
Well,
I mean, literally.
Like I said, I quite happily come onto yours and we can talk about loads more of it.
I mean, like I say, and this is only a small portion of what I actually have. I mean, I've not even grazed the surface of what I could tell you about what I've captured over these days filming and stuff. And it's not just putting an observation out and saying, "There's an observation, that's me done." You know, this is proper analysis of all the observational things that have gone into it. You know, measurements, everything. I've not done the temperature gradients, although I have actually started to be doing that.
That's I think the most important
thing. I have actually started to do that. But one thing that I forgot what I was going to say now. I can't remember. Never mind, forget it.
But Ranty, here's what I suggest is, like, use your observations that you've already taken, the data that you've already taken, and just pick a random spot and make a prediction without doing the observation. Just make the prediction first. You say, okay, the Earth is flat. We know this building to be this far away from this observation point at this height. And you're going to go out there and say, I predict to see this a certain amount off the horizon or a certain drop. You can compare it to days where you've taken it that are similar in barometric pressure, temperature gradient. All that information is pretty much available online through weather.com and dateandtime.com. A lot of those websites will give you the information locally. And make a prediction and see if your prediction holds. If your prediction holds, it'll strengthen your resolve that the Earth is flat. If it does not, then it should make you wonder whether it is something else other than flat.
Well, maybe next time we'll get into shoaling, which will help explain a lot of the last observations that you were pulling up. We'll get into that at some point, I'm sure, and it's pretty easy to understand, and there's a pretty easy explanation for why you see things apparently going beyond an actual curve.
Right. So just before we go on, I've got this one observation that I've been demanded to show you. It's Red's Rhetoric's observation of Tampa Bay. Yes, demanded. So he took a photo of Tampa Bay, and then compared it with a photo that was taken a lot closer up. And it shows that when you're further away, even though the proportions of the buildings and everything are the same and there's no inferior miraging and stuff, that there's just a physical blockage. How do you explain this observation?
Sinking.
Because of what? What's causing the sinking?
Refraction.
Yeah, can you explain the mechanics of that? Like,
We've just been through it. We just spent the whole show going through it.
yeah, but I mean, there would have to be a particular temperature profile that would cause that.
Well, yeah, we're very low to the water,
Hey,
as you can
Fight,
see. I mean,
Fight,
ahead.
Ranty, let me make a suggestion, because this is a completely different observation topic that deserves a real well thought out conversation. I know you said you have to go here shortly, and I don't know if we'll have enough time to really cover this. Plus, we can bring Red on to talk about it, since he's the one that actually made the observation, if that's okay with you, Ranty. And then and Red, of course.
Yeah.
No, fuck that. We're just gonna tell Red to show up. He'll be there. No, but at least we can set it up to have a proper conversation about that, and you can talk about other aspects like the shoaling that you wanted to bring up and whatnot. We can set that up for a future date on Fight's channel, if that's all right with you.
Mandevil in the chat says, for Ranty, how do you feel when you watch one of Conspiracy Cat's videos and songs about you?
yeah, just laugh. End of the day, it's one of them, innit? You know,
He's quite
can't
funny.
stop people making videos about you. Yeah, he's one of the better ones, better than Simon Dan.
Oh, throwing shade at Simon Dan there. Okay, and then
although Simon Dan has started to rip him off a bit. He's started to rip him off a little bit. He started to copy him. But
Conspiracy Cats is the one that convinced me to start my channel.
He's still a prick. But, you know.
I love the guy. I think he's brilliant.
Now, yeah, like I'm thinking in myself, now I know who I need to blame for all this shit that I've been through in the past year.
Bella Charge for $2 New Zealand dollars says, do you not have to presuppose that the Earth is flat?
No. We just see things. We don't need any explanation other than we see things.
You see things, but you don't need an explanation.
Yeah, we just see things.
That needs an entire conversation.
That's it. We see that building.
Wouldn't you say that?
Tell us it's loomed up. You tell us it's loomed up, and we go.
But wouldn't you say
what,
that?
Really?
But when you say that your presupposition then would be that you're presupposing that the pre-drawn conclusion that you come to based on an ignorant observation. And I'm not saying that negatively. I'm saying like you don't have any data. You say you look with your eyes. You really, at that point, if you just look out and see a building, you don't know how tall the building is. You don't know how far away it is. You're just making an ignorant observation with no data, and you're coming to a conclusion. I would say the presupposition for you and most flat earthers is that conclusion that you're coming to. You're presupposing the conclusion and using an ignorant observation to support that conclusion.
I wouldn't say so, because when you were born, when I was born, when Craig was born,
I was created in a lab.
You were created in a lab, which is fine. But ultimately, you were told that we live on a spinning ball. You weren't given the option to just go out and explore for yourself. Now, I would hazard a guess that had you never been told that the Earth was a spinning ball, and you'd just been able to grow up naturally, going out, enjoying yourself, playing out in the outside, and somebody asked you what shape the Earth was, you would never in a million years have come up with a ball.
I think after my physics degree, I would have.
Hold on.
No. I mean, if you never had anybody telling you what the shape of the Earth, so that's no teachings, no going to school.
Physics doesn't teach me that the Earth is a ball. It gives me the ability to deduce that myself.
But,
right. So,
listen,
so my belief in the Earth being the shape that it is doesn't come from the pictures from NASA. Okay. So I've tried to stay away from photographic evidence of things because I believe that most photographic observations are just they're not well defined. They don't have all the data that comes with it that would be needed to say yes, this is a globe, or yes, this is flat. I think it's just an observation. So what I've come to the conclusion, how I use my observational reality around me is simply by looking at the sun, seeing how the sun does not change in size. as it approaches me or goes away. It does not change in apparent speed as it approaches and goes away from me. It doesn't, there's no way to explain observations from the southern hemisphere of the sun. I'm not even going to talk about the southern stars right now, of the sun from the southern hemisphere. I have family down there that have verified that on the equinox, you can see it rise due east. Okay, I just asked them for it, said, hey, and this was last year. I said, hey, can you guys go out and just tell me, does it rise due east? And they went out, rises due east. I said, okay, great. That's all I need to know. I didn't think my family lied to me. I presupposed they were telling me the truth. But at the same time, I just asked them to do that for me while they were down there. Okay? Those observations help me come to the conclusion that the Earth is not flat. That's all I need to come to the conclusion that it's not flat. I don't see the way the North Star conforms to the surface of the Earth through observation from the thousands of years of sailors doing it. I would believe that that's the only way for that to be successfully used by sailors would be if the Earth was shaped like a globe, not flat, not a cube, not a octahedron or whatever, a 20-sided dice or whatever the case may be. It's generally spherical. It has a rough surface on top of it, so it kind of keeps us from making exact measurements. It has an atmosphere in it that causes refraction, causes things that we just can't, like, we can quantify it, but it's never going to be an ideal observation. We're not, like you said earlier, there's no way, even though when I said, hey, you know, if it goes through this line, it's perfectly straight, it goes through the straight band, you were actually kind of right. That's only under ideal circumstances. That's only under the circumstance that you and I are talking here saying, let's assume that that's perfectly, you know, the pressure, temperature, everything in it is completely the same, which we know not to be true. We can only generalize that based on, you know, ideal circumstances. So my point being is that there's a lot that we can learn from this, you know, like all of us. I think you are in a position to not take what I say, not take what Fight the Flat Earth says, but to make your own observations and come to your own conclusions. Just try to do it without presupposing the shape of the Earth. Just make a prediction, see which one fits, and go start your journey from there.
Right. Okay. Moving on to the
rant.
moving on to the next one. We've got David Oliver for £5 says, get Ranty to provide evidence of a flat Earth, real evidence, not made up fantasy. Well, all of Ranty's observations are on his channel. And you know what, guys? I would even encourage people to go and subscribe to Ranty. As a flat earther, I think he's going out and doing the observations, and it's worth having a look at what he's done. So if you want to see any of Ranty's evidence, just go to his channel. Hugo Perez for $5 says, Ranty just wants to make observations near water like Samuel Rowbotham, you cheater.
No, I had a bit of back and forth with Mick West a couple of years ago, 2.5 years ago, and he said that he could take an iPhone up to the top of Blackpool Tower and see the curve, just take a photograph of it. So I did. I went up, I took an iPhone, I took a P900, and I took a Samsung Galaxy. So I took three images. And what do you know? We didn't get any curvature. And I put the video out, and Mick West didn't come back to me. And then it was transpired that you can't see curvature from under 120,000 feet. So what can I say? Mick West tried his best, but he didn't actually make that claim very good, did he? I mean, you have a field of view.
It depends on the field of view and the conditions. I don't think there's any particular height that you can see it at. But anyway, Fargoth92 for $2 says, Flat Earthers' main problem is they're frickin' dumb. Okay then. Free1 for $2 says, Ranty's lack of understanding is astounding. Well, at least he's having a decent conversation.
Right, cheapskates here though. $2, £1. What's going on here? I mean, come on. At least what you know. The guys that come over on my channel when they super chat, it's $20, $50. I mean, you're just getting the cheapos here. Come on, guys. I mean, you guys been going for 3 hours and more, putting a show on, and you're giving him $2, you cheapskates.
Thanks, Ranty.
Get your hands in your pocket.
Oh, no, man. No. Those guys are amazing. We love the people that support us.
Show some.
I appreciate every super chat, guys. Obviously, it allows me to keep doing this.
But every time I hear donated $2. Has donated $2. I mean, the $2 add up, sure, but come on.
We got Rachel S. Lodian for 10 Australian dollars. Just gave a #1 fan sticker. Thank you, I appreciate it. Inciter for 20 Donkey Kongs. Ranty, is it possible you are wrong?
Of course, it's possible that there's no certainties in life at all. But I'm yet to see, like I say, I'm yet to see the proof that's going to convince me that we live on a globe. It's as simple as that. I have been asking for it, and I've been waiting. I want somebody to show me that looming can happen. If somebody can demonstrate,
I'm going to work on that because I've got an idea for something that I can do.
Yeah, if somebody can demonstrate looming to me, demonstrate it. Show an image being lifted up in proportion over some water, right, into the camera. If they can show me that, yeah, you might have a point. Until then, no.
Right. Well, I'm going to be working on something, so I'll get back to you. And we've got Song 13 and Fohammer335 are both new members. Thank you very much, guys. Jaybird Max for $2 says, any horizon at all proves the Earth is not flat. Yeah, horizons, love them. BK Rich for $2 says, Ranty, do you watch Conspiracy Cats? Yes, he's already said he does, and he thinks he's a dick. Anthony Purcell for $2 says, seismic arrivals show Earth is round. I did a video. Yeah, what do you think about PNS waves and stuff?
PNS waves, well, the idea that what is it? They go through. Some of them go through water. Some of them go through or hit a rock and return. They can give false positives, can't they? It's like Quadrilla did the same sort of technology to try and find out what was happening at the gas and oil place down where we are, and they couldn't even get it right. A couple of 100 feet down, they were getting things wrong. I mean, when they dug the Cola Super Deep borehole, they predicted how they would find everything on these layers on the way down with the same technology that you're showing here. And of course, when they actually dug the hole, they found that it was nothing like they anticipated it to be. In fact, it was completely different. They found water down at a depth they didn't expect. So I don't know. I mean, to me, it's an inconsistent science.
Interesting. That's an entire other conversation. So I've been looking into seismology as well, but it's getting late, so we're going to crack on. Galby3000 for £2 says, check my DM in Discord to see video showing curve. Again, I'm sorry, I've got so many Discord messages, I can't get to them. J.O. Warren for $4.99 says, anyone else think Ranty looks like Pepper from AHS Carnival, or just me? I don't know what that is, so possibly. Glass Monster for $2 says, team, send me one of those Team Skeptic minifigures. You got minifigures, team?
Yeah, I don't know what minifigures he's talking about, but I need one if there's one out there. I gotta get, man, that's something that needs to happen. We need to make some Team Skeptic minifigures so I can send Ranty one free on the house. I'll even pay for shipping. I'll send it to a P.O. box. You can put it up in your videos. I'll send you a personal one.
Ranty,
what's that?
I said I've got a golf club I could use it on.
I'll make you some Team Skeptic tees then, so you can throw the balls on top. You can hit the globe off the top of my head.
Ranty, what do you think of my Sleeping Warrior figure?
Yeah, that's pretty accurate, actually. You've not got him. He's willy out. He's not pissing into a jar, though, is he?
Oh my God.
Hey, okay, yeah, that was my question, Ranty. That's my question for you. Okay, because Sleeping Warrior, he started to own it, and then I think he realized how dumb it was, and then went away from the ownage of his pissing on stream. Do you think he peed on stream, or do you think he actually did the medicine for his dog, like he says?
To me, it's well.
To me.
Obviously, people can be wrong, so I can be quite wrong here when I say this, but it sounded to me like he pissed in it. What can I say? That's what. It's just.
It absolutely did. It sounded like.
I don't know.
You're a human being, Ranty, right? Like me and Fight the Flat Earth, you're a human male that pees and knows the sound of piss going into a container. And that was absolutely urine going into a fucking, I'm sure it was like a Mountain Dew bottle.
It was those little squirts, like the that's he was pissing in the bottle.
To me, it was the twitch in his left eye when he was done. The little shiver with his shoulder. That's when it did it for me. I was like, when he was like, Oh yeah, okay. All right, I'm back.
But,
And they're like,
but
yeah,
like
I
I
was like,
say,
yeah, he pissed. He just shook off.
I
in
could
the
be
bar.
wrong. Who knows? We'll never know. We just have a sound effect, so it's
Yeah.
just one of them. We can speculate, can't you? So.
They've got a couple more super chats. John Rapp for $2 says, cheap, 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 cheap. Yeah, you cheap bastards. Keep them coming. I love you all. And Glass Monster for $2 says, Team Skeptic logo minifigures. Yeah, we should totally get those.
At the Lego minifigures, we need to make that happen, man. We really do. So whoever's out there that's artistically inclined, because I'm not. You saw my paint today. I'm not. There's people telling me I can draw perfect circles and straight lines by holding shift. Thanks for that advice. Like 2 hours too late, guys. But I had a good time though. This was great.
Yeah, Galby, it's just getting a bit late. I could show some more another time. Sorry. Right, so that's all for now. We've finished the super chats. Honestly, Ranty, thank you for coming on. I really do appreciate it. And thank you for being civil. Some flat earthers can be extremely difficult to talk to. So you've actually gained a couple of subs according to my chat. They subbed you just for that burn against Riley. So
Awesome. Thanks very much.
No worries.
I don't think I'm very pleased that I have more subs than him. I think that
this is what I noticed, that you and him fell out about the time you passed him in subs. I think it's just him throwing a hissy fit.
Possibly, yeah. And him always being wrong.
Yeah. Any final words before we shut down for tonight?
No, thanks for having me on. Thanks to all the people in chat who clearly think I'm an idiot, but thank you anyway for listening. Yeah, go pop over and subscribe.
Ding.
You know, I mean, ultimately, you can come on if you want to come and have a chat. I have an open panel over there, so if you want to come and you want to have a chat with me or some of my flat earth friends over there, you can get into it. It's all very civil. It's a bit like this, and you know, there's never any real animosity. Sometimes it goes down a little bit, but you know, we can't stop people from being people. But for the most part, we're a pretty nice bunch of people over there. You know, come over, tell us why the Earth's a globe. You know, that's what we want to hear.
Awesome. I think me and Team would probably be willing to come over and have a chat with you and some other guys. Definitely. You've been decent enough tonight, and like I said, I really do appreciate that. So yeah, guys, if you feel like checking out Ranty, he's removed Flat Earth from his name. He is just Ranty. Why did you do that, Ranty?
There's two narratives. The first easy one, which is basically that it's easier for me to read comments. Yeah.
Oh, he just dropped out for a second again. Blood neck.
How was that?
Yeah, there you go. He's back.
Right. So why did I do that? Right. So the first one is that when I'm getting comments in the chat goes quite quick. Quite often it takes, when people just call me Ranty, they don't type Ranty Flat Earth, so it doesn't pop up in red, so I don't get the option to see it. So I quite often miss what they're actually trying to ask me if they need to ask a guest a question. So it's by shortening it, it's made it a lot easier for me to see their comments. And ultimately as well, I mean, at the moment, the belief in the flat Earth at the moment is that this quote unquote virus, which probably isn't a virus, it's just a biological weapon that's going around. They don't believe it's real. I actually believe it is a real thing. It is actually killing people. And, you know, so I've removed that because ultimately it's the flat Earth belief that there's nothing going on. It's just a drill. It's a hoax. Me personally, I believe it's absolutely real and that people are dying, and I've been going on about it for 10 weeks and I've lost a bunch of subscribers over it, but hey ho, you know, no, it is what it is.
It's definitely real. I would disagree about the biological weapon thing. I do think it's just some assholes eating things they shouldn't and causing things, but whatever has caused it, it's definitely a real fucking thing that is killing a lot of people. So everyone, please wash your hands, follow the social distancing measures that are put in place. It's not a drill, Sleeping Warrior, you fucking idiot. And just stay safe. I'm going to do my best to keep you entertained while we're all in lockdown. I know Team's doing the same. Team, any final words before we shut up for tonight?
Yeah, I can't find my goddamn dinger. You just called him. There it is.
Ding.
What happened? I played it and it didn't work.
Hey.
So that was for Sleeping Warrior. I would have dinged you earlier, Ranty, when you said that people call you an idiot or think you're an idiot, but I didn't ding you because I couldn't find my dinger at the time. Yeah, my final words are going to be thank you, Ranty. I had a great time tonight. I think it was awesome that you came on and had that conversation. I hope you come on more because, like I said, if there's anybody out there that is making measurements and doing stuff, whether I believe you're coming to the right conclusion from your measurements or not, that's a whole different topic. The fact that you're out there actually trying to make measurements, it gives you a lot more respect in my book than a lot of these people that sit at home with in whatever fucking cardboard box they can get an internet connection and electricity to, saying that the earth is flat and how the whole world is against them. Those people are morons and idiots, and just they don't deserve the same platform that you do, trying to make observations. I still think you're coming to the wrong conclusion, but hey, that's just a difference of me and you and what you're doing. So I appreciate that you at least do it.
It'll be a slow process to bring you guys over to the flat Earth, but I hope to do that at some point. I've got plenty of observations and proof that may well convince you at some point. I'm sure I can probably explain 97 to 98% of observations that I've seen. So, and that's just using the topography of the land, shoaling.
Right. Well, here's the challenge for when I come on your show. Then, right? I've not seen an observation that isn't explainable on the globe Earth. Try and get me some observations that you think you have that cannot be explained by the heliocentric model.
Well, that is going to be impossible because you have something called an infinite over 6 refraction. That's it. So it doesn't really matter. You've just got a slidey scale that you can say more refraction, more refraction. I could show you a shore-to-shore observation 200 miles across, and you would still claim that it's refraction that's bringing that back. So what can I say? There's no observation that I could show you that couldn't be explained on your model.
Let me add to that because you did say earlier that you've made that one observation shore to shore many times, or you've tried to make the observation shore to shore many times, and you can't. You say that on some days it's optimal and you can, on some days it's not, and you can't. Mm-hmm. Explain that without refraction then. Because if we're using refraction to explain certain things, then you can't say, well, you're not able to use refraction, but here, let me use refraction when I want to explain my observations. Other than than to say this is the reason why you can't.
Well, it's pretty simple. When you get the really clear images, you're seeing things that you shouldn't see on a globe. It's as simple as that. So they are being loomed up. They're being refracted around to see. The days that you go out and you see all the muck and the distortion and the inferior mirages and things like that are just in your way, they're the days that it's perfect for the globe. So, you've got to look at it from, I do. It's a very, very simple thing. On nice clear days with good weather, no distortion, you see a very long way. Whereas all the other times that you film and you see these obstructions, that you see these inferior mirages that are blocking things, that for you is your curvature. And my channel is about debunking that claim that these obstructions are curvature. And I think I've got a good handle on being able to explain away what you see as claims of a curvature, because you can easily explain them with shoaling. Shoaling's one, it's a massive thing. We didn't get to talk about it today, but it is a massive. There's even a shoaling calculator out there that will show you these effects and what actually happens.
Okay,
Something's very interesting to look into.
There's definitely stuff that we can continue the conversation on.
Yeah, share that calculator with Fight so that way he can share that with me. Yeah.
Yeah. Just email that to me when
just
you get
Google
it.
You can do that later. You can do that later. Yeah.
But just a couple more super chats.
I just want to make sure I was using the same one.
Anthony Purcell for $2 says, thank you, Ranty. And then we've got Esteban Elebaca for 5,000 CLP. I think that's Chilean pesos. Says, Ranty, I hope you take on Team Skeptic idea to make predictions. You'll finally get that a strong density gradient over a few meters in elevation will produce a lot of refraction, no distortion, only bendy light. Interesting. Anything to
I wish
say
that
to
was the
Randy?
case, because Yeah, I wish that was the case, because since I had the P1000, basically when I had the P900, which was a lesser camera, I got beautiful observations, but it wasn't in 4K. I get the P1000, and it's just mush all the time. There's barely been a day where I've had a good observation, so it's all just been inferior mirages and stuff like that. I wish I'd had the P1000 2.5 years ago. Unfortunately, not the case.
Oh, well, I'm glad you've got it, because you're doing the observations, and that's the important thing. So again, thank you, Ranty, for coming on. Thank you, team, for being here to back me up as always. And thank you, everybody, for watching. If you're not able to support me with a super chat or becoming a member, the best thing you can do to help the channel is to share it on all the social medias, the Facebooks, the Twitters, the Bebos, the MySpaces, all that. Thank you, everyone, for watching. Be sure to check out Ranty's channel, and I will be back hopefully on Friday with another debate and then another video on Sunday.